Hello there, and welcome to Science for Sleep, the place where curiosity slows down, questions take their time, and science becomes something you can gently drift off to. Tonight, we're going to explore a question that sounds simple at first, but becomes more surprising the longer you think about it. What is the hottest place in the universe? At first glance, the answer might seem obvious. You might picture the sun, blazing high in the sky, or perhaps molten lava spilling from a volcano. Maybe you imagine the surface of a distant star glowing white-blue with unimaginable heat. All of those sound like reasonable guesses, but the truth is a little stranger. The hottest places in the universe are not always the ones that look the brightest. Some are hidden in violent cosmic events, others exist only for tiny fractions of a second, and a few of them are so extreme that they push the limits of physics itself. Tonight, we're going to take a slow and careful journey through those places. We'll start with the kind of heat we understand here on Earth, the warmth of sunlight or the heat of a summer afternoon. Then, step by step, we'll travel outward into the wider universe, moving toward environments so hot that atoms break apart and matter behaves in ways that sound almost impossible. But before we wander too far into cosmic furnaces and exploding stars, I'd like to ask you something simple. Where are you listening from tonight? Are you curled up somewhere quiet after a long day? Maybe in your room with the lights dimmed, or under a blanket while the world outside slowly settles down. Perhaps it's late evening where you are. Or maybe you're listening in the early hours of the morning when everything feels a little calmer. And what time is it in your corner of the world right now? It's always a little amusing to think about that. A video like this travels across the planet instantly, yet each of us arrives here at a completely different moment of the day. Some listeners are ending their evening, others are just starting their night. A few might even be listening while the sun is rising somewhere far away. Wherever you are, I'm glad you're here. If you find this kind of slow exploration relaxing or interesting, feel free to give the video a like and perhaps subscribe as well. It helps this quiet little space reach more curious minds who might also enjoy drifting through science at a gentler pace. Now, hopefully this topic won't keep you too awake, although, if it does, at least you'll learn something unusual about the universe before sleep arrives. So go ahead and settle in, let your thoughts slow down, and let's begin with a simple idea: heat. Most of us experience heat every day without thinking about it very much. You feel it when you step outside on a sunny afternoon. You notice it when you hold a warm mug of tea or coffee. In winter, you appreciate it when a room heater starts working after a cold walk outside. Heat is one of those everyday experiences that feels very familiar. Yet the deeper scientists look at it, the more interesting it becomes. When we say something is hot, what we really mean is that the tiny particles inside it, atoms and molecules, are moving quickly. Temperature is simply a measure of how energetic those particles are. The faster they move, the hotter something becomes. Take a pot of water on a stove. As the burner heats the pot, the water molecules begin moving faster and faster. Eventually they move so quickly that they break free from the liquid and turn into steam. Nothing magical happens there. It's just motion at a microscopic level, and that simple idea, particles moving faster and faster, turns out to be the key to understanding the hottest places in the universe. Because if you keep adding energy, particles keep speeding up. If they move fast enough, atoms themselves begin to break apart. Electrons separate from nuclei. Matter becomes a kind of energetic soup called plasma. And if the temperature rises even further, the behavior of matter changes again. But we're getting ahead of ourselves. Before traveling out into deep space, it helps to consider the range of temperatures we're familiar with here on Earth. Let's start with something comfortable. A pleasant room temperature might be around 20 degrees Celsius, or about 68 degrees Fahrenheit. At that temperature, the atoms in the air around you are moving at hundreds of meters per second, even though you don't notice it. Warm summer days might reach 30 degrees Celsius. Hot deserts can climb past 40. Those temperatures feel intense to us, mostly because our bodies are very good at maintaining a stable internal temperature. Humans function best around 37 degrees Celsius. When the environment gets much hotter than that, it becomes harder for the body to cool itself. But compared to cosmic temperatures, even the hottest places on Earth are surprisingly mild. Consider lava flowing from a volcano. Molten rock can reach around 1000 degrees Celsius. Standing near it feels like standing beside a giant open oven. That's already far beyond anything comfortable for living creatures, and yet 1000 degrees is still small compared with the heat of stars. The surface of our Sun, for example, is about 5500 degrees Celsius. At that temperature, matter behaves very differently from the solid rocks and liquids we're used to. The Sun is made mostly of plasma, a state of matter where electrons are no longer tightly bound to atoms, but even the Sun's surface is not the hottest part of it. Deep in the Sun's core, temperatures climb to roughly 15 million degrees Celsius. That enormous heat allows hydrogen atoms to fuse together, releasing energy that eventually becomes sunlight. Every beam of sunlight that warms your skin began its journey in that furnace at the center of our star. Even so, the Sun is not the hottest star in the universe. Far from it. There are stars many times hotter. Some massive blue stars have surface temperatures of 30,000 degrees Celsius or more. These stars burn brighter and hotter because their immense gravity squeezes their cores harder, allowing nuclear reactions to occur at faster rates. Yet as extreme as those numbers sound, they still don't come close to the most intense temperatures known in the cosmos. Because stars, it turns out, are only one step along a much larger scale. Elsewhere in the universe, there are events where matter becomes far hotter than the surface of any star. Exploding stars, collapsing stellar cores, and swirling disks of gas around black holes can all reach temperatures that push far beyond what most people imagine. Some of those environments heat matter to billions of degrees. Others briefly reach trillions, and one of the hottest conditions ever created didn't occur in space at all. It happened here on Earth. But before we reach that moment, it helps to take a closer look at what temperature actually measures. Because temperature, despite feeling simple, is one of the most useful tools scientists have for understanding the universe. Every object around you has a temperature. Your room, the air outside, the distant moon, even the empty space between galaxies has a measurable temperature, although it is extremely cold. In physics, temperature tells us something about energy distribution among particles. When energy is added to a system, particles move faster or vibrate more strongly. When energy is removed, their motion slows. This idea applies everywhere, from a cup of tea cooling on a table to entire galaxies, interacting across millions of light years. But measuring extreme temperatures is not always easy. You can't exactly place a thermometer into the core of a star. Instead, scientists rely on indirect methods. They study the light emitted by hot objects, analyze radiation patterns, and use physics equations to estimate temperatures from observed behavior. For example, very hot objects emit light at specific wavelengths. By studying that light, astronomers can determine how energetic the particles must be, which reveals the temperature. In other situations, scientists observe how matter behaves under extreme conditions. If particles are moving with certain energies or colliding in specific ways, those interactions can also reveal temperature. These techniques allow researchers to estimate temperatures across the entire universe, from frozen clouds of gas drifting between stars only a few degrees above absolute zero, to violent explosions where matter becomes so energetic that atomic structure barely survives. So when we ask about the hottest place in the universe, we're really asking where particles are moving with the greatest energy. And the answer turns out to be more surprising than simply pointing to a star or a galaxy. Some of the hottest environments occur during brief cosmic events. A star collapsing into a neutron star, for example, releases enormous amounts of energy. During those moments, temperatures can climb to extraordinary levels. Similarly, when matter spirals into a black hole, it forms an accretion disk. a swirling ring of gas heated by intense friction and gravity. Those disks can reach temperatures of tens of millions of degrees. That's already far hotter than the sun's surface, but even those environments are not the ultimate champions of heat, because there are places where the universe briefly reaches temperatures that approach the conditions present shortly after the Big Bang itself. And strangely enough, one of those places exists in enormous underground laboratories where scientists smash particles together at incredible speeds. Those experiments recreate tiny flashes of the early universe, producing temperatures far beyond anything naturally found in our solar system. We'll get to that in a while. For now though, it helps to keep our journey grounded in something familiar. Because before we explore collapsing stars, black holes, and the hottest matter ever created, it's worth thinking about the way humans experience heat here on Earth. After all, the concept of temperature only became meaningful to us because we could feel warmth and cold long before we understood physics. Humans have always been aware of heat. The warmth of fire helped our ancestors survive cold nights. The heat of the sun allowed crops to grow. The absence of warmth during winter shaped entire cultures and migrations. Long before thermometers existed, people could sense temperature through touch and experience, and over time, that everyday experience slowly evolved into the scientific idea we now call temperature. Understanding how we perceive heat is actually an important step toward understanding how scientists measure it across the universe. Because the way our bodies interpret warmth and cold reveals something about the limits of our perception. For example, what feels extremely hot to us might be only a small increase in temperature on a cosmic scale. A summer heat wave might push temperatures to 40 degrees Celsius. That feels intense. But compared with stellar temperatures, that difference is barely noticeable. It's similar to the difference between walking speed and the speed of light. Both involve motion, but the scales are vastly different. The same is true for heat. A simple way to begin thinking about heat is to remember that long before thermometers, satellites or physics equations existed, humans were already experts at feeling it. You don't need any scientific instruments to know when something is warm. Your skin tells you immediately. Step into sunlight on a cool morning, and the warmth feels pleasant. Touch a metal pan that has been sitting on a hot stove, and you will pull your hand back in a fraction of a second. Walk outside on a summer afternoon when the air feels thick and heavy, and you instinctively slow down, searching for shade. For most of human history, that kind of sensory experience was the only way people understood temperature. Warmth meant comfort. Cold meant danger. Heat could cook food, soften metal, and keep predators away at night. But too much heat could also destroy things. Forest fires, droughts, and scorching deserts reminded early civilizations that warmth was both a gift and a force to be respected. Even today, despite all the advanced tools we have for measuring temperature, our first encounter with heat is still personal and immediate. It begins with the body. Your skin is covered with tiny nerve endings that detect temperature changes. These specialized receptors respond when the environment around you becomes warmer or colder. They send signals through the nervous system to the brain, which then interprets the sensation. That is why you feel warmth almost instantly when holding a mug of hot tea. The molecules in the cup are vibrating more quickly than the molecules in your hand, and that energy begins to flow from the hotter object into your skin. Your nerves notice the difference and report it. From a physics perspective, heat is simply energy moving from a warmer place to a cooler one. But from the perspective of a person sitting quietly in a room, it feels much more like a sensation than a transfer of energy. Your body, interestingly enough, is constantly managing heat whether you notice it or not. Humans function best within a very narrow internal temperature range. The average human body maintains a temperature of about 37 degrees Celsius. That number may vary slightly depending on activity level, time of day, or even individual biology, but the general range remains surprisingly stable. To keep things that way, the body uses several built-in systems. When you become too warm, your body begins sweating. Tiny droplets of water appear on the skin and slowly evaporate into the air. That evaporation removes heat, cooling the surface of the body. At the same time, blood vessels near the skin expand, allowing more warm blood to circulate close to the surface where heat can escape into the surrounding air. When you become cold, the opposite happens. Blood vessels near the skin tighten, conserving heat by keeping warm blood deeper inside the body. Muscles may also begin to contract rapidly in the form of shivering, which produces additional heat through movement. All of this happens automatically, without any conscious effort. You might simply notice that you feel hot, or cold, or comfortable. Behind the scenes, your body is constantly adjusting. These small biological responses shape the way humans perceive temperature. Because our bodies operate within such a narrow thermal range, even modest changes in the environment can feel dramatic. A room that is 22 degrees Celsius might feel comfortable. If the temperature rises to 30, the difference feels intense. Yet on a cosmic scale, both of those numbers are extremely close to one another. Still, for humans, those few degrees matter a great deal. Think about the experience of stepping outside during different seasons. In winter, when cold air touches your skin, the sensation can feel sharp and immediate. Breath becomes visible as warm air from the lungs meets the colder atmosphere. Fingers stiffen. Shoulders rise slightly as the body instinctively tries to conserve warmth. Then there is the opposite experience. A summer afternoon when the sun stands high in the sky and heat radiates from pavement and buildings. The air feels thick, movement slows, even standing still can feel like work. What you're experiencing in those moments is the interaction between your body and the surrounding environment as energy moves between them. And on Earth, the largest source of that energy is the sun. Nearly all warmth on our planet begins with sunlight. The sun releases enormous amounts of energy in every direction. Only a small fraction of that energy reaches Earth, but it is more than enough to power weather systems, ocean currents, plant growth, and the delicate temperature balance that allows life to exist. Sunlight travels through space as electromagnetic radiation. When it reaches Earth, some of it is reflected back into space by clouds and ice. The rest is absorbed by land, water, and atmosphere. Once absorbed, that energy becomes heat. The ground warms, air currents begin to move, oceans slowly store and release thermal energy across seasons. In a sense, the warmth you feel on a sunny afternoon is the final step in a long journey that began deep inside the sun millions of years ago. But the experience of heat on Earth is not just about sunlight. Geography also plays a role. Different regions of the planet absorb and release heat in different ways. Deserts, for example, are famous for extreme temperatures. During the day, the ground absorbs large amounts of solar radiation. Sand and rock heat quickly because they contain little moisture to slow the process. Temperatures can climb above 50 degrees Celsius in some locations, yet at night, deserts cool rapidly. Without clouds or water vapor to trap heat, energy escapes back into space. A scorching desert afternoon can turn into a surprisingly cold night within hours. Oceans behave differently. Water warms more slowly than land because it has a higher heat capacity. That means it takes more energy to raise its temperature. As a result, coastal regions often experience milder climates. The ocean acts like a giant thermal reservoir, absorbing heat during warm periods and releasing it gradually when temperatures drop. This steady exchange of heat between land, water, and atmosphere creates the weather patterns we experience every day. Wind carries warm air from one region to another. Ocean currents transport heat across entire continents. Clouds trap heat during the night and reflect sunlight during the day. Even something as simple as standing in the shade beneath a tree is part of that larger system. Shade works because objects block sunlight before it can reach you. Without direct radiation from the sun, the air and ground around you transfer less heat into your body. The difference might only be a few degrees, but to human senses it can feel dramatic. Throughout history, people have adapted to these temperature patterns in creative ways. Architecture in hot climates often includes thick walls, narrow streets, and shaded courtyards that help reduce heat exposure. In colder regions, homes are designed to trap warmth and minimize heat loss. Clothing choices also reflect the need to manage temperature. Light fabrics allow air circulation in warm climates. Insulated layers help retain heat in colder ones. All of these strategies are part of humanity's long relationship with heat. Fire, perhaps more than anything else, changed that relationship permanently. When early humans learned to control fire, they gained the ability to create heat wherever they needed it. Fire provided warmth during cold nights, protection from animals, and a way to cook food. Cooking itself transformed human diets. Heat breaks down tough plant fibers and proteins, making food easier to digest and unlocking more nutrients. Some anthropologists believe that the regular use of fire played a role in the development of larger human brains by improving energy intake. A small flame might not seem very impressive today, especially in a world filled with electric stoves and modern heating systems. Yet in ancient times, fire represented control over one of nature's most powerful forces. Even now, fire remains one of the hottest phenomena most people will encounter directly. A typical campfire burns at temperatures between 600 and 1000 degrees Celsius. Industrial furnaces can reach much higher temperatures, sometimes exceeding 2000 degrees Celsius depending on the fuel and design. Those temperatures are enough to melt many metals and reshape materials, and yet, compared with the heat found in stars, even the hottest furnace on Earth is relatively mild. This contrast between everyday heat and cosmic heat is one of the most fascinating aspects of astrophysics. The warmth you feel on your skin from sunlight comes from a star whose surface temperature is thousands of degrees. But even that star is not the hottest object in the universe. Far from it. Before we venture out toward those extreme environments, there is one more important idea worth considering. Human perception of heat is not perfectly reliable. Two objects at the same temperature can feel very different when touched. For example, a metal chair and a wooden chair sitting in the same room will both be at room temperature. Yet when you touch them, the metal often feels colder. This happens because metal conducts heat more efficiently than wood. When your hand touches metal, heat from your skin moves quickly into the material, creating the sensation of cold. Wood transfers heat more slowly, so it feels warmer even though its temperature is identical. The same principle explains why walking barefoot on tile floors feels cooler than walking on carpet. Your senses are detecting the rate at which heat moves, not just the temperature itself. Because of this, humans eventually developed tools to measure temperature more accurately. Thermometers allowed scientists to quantify heat rather than simply describe it. Early thermometers used expanding liquids such as mercury or alcohol. As temperature increased, the liquid expanded along a calibrated tube. Later technologies introduced electronic sensors capable of detecting extremely small temperature changes. Today, scientists use instruments far more sophisticated than those early devices. Infrared cameras can measure heat from a distance by detecting thermal radiation. Satellites monitor temperature patterns across entire planets. Sensitive detectors can even measure the faint heat left over from the early universe itself. These tools allow researchers to compare temperatures across enormous ranges, from the cold darkness between galaxies to the blazing interiors of stars. But all of those measurements trace back to the same fundamental idea. Temperature reflects the energy of moving particles. That simple concept links the warmth of sunlight on your skin to the most extreme environments in the cosmos. And once scientists understood that connection, it became possible to ask a much larger question. If heat comes from particles moving faster and faster as energy increases, then somewhere in the universe there must be places where those particles move with incredible energy. Places where atoms are torn apart. Places where matter glows with blinding intensity. Places where the word hot barely captures what is happening. To explore those environments, scientists first had to develop reliable ways to measure temperatures far beyond anything experienced on Earth. At some point in history, people began to realize that warmth and cold were not just sensations. They were physical properties of the world that could be studied, measured, and understood. For a very long time, heat was mysterious. Ancient thinkers had many ideas about what it might be. Some believed warmth came from a special substance that flowed between objects. Others imagined heat as a kind of invisible fluid that filled materials and escaped when something cooled down. Those ideas sound unusual now, but they made sense at the time. When a metal rod becomes hot on one end and gradually warms along its length, it can feel as though something is travelling through it. Eventually, though, experiments revealed a simpler explanation. Heat is not a substance. Heat is energy in motion. More specifically, temperature reflects how quickly the tiny particles inside matter are moving. Every solid, liquid, and gas is made of atoms and molecules that are constantly vibrating, spinning, or bouncing around. Even objects that feel perfectly still are filled with microscopic activity. When those particles move slowly, the temperature is low. When they move faster, the temperature rises. This idea may seem straightforward, but it took centuries of observation and experimentation before scientists fully accepted it. One reason is that the motion involved is incredibly small. You cannot see atoms moving with the naked eye, so for most of human history their behaviour remained hidden. Once scientists began developing tools to study matter at smaller scales, the picture became clearer. Consider a simple glass of water sitting on a table. From a distance it appears calm and motionless, but at the microscopic level, every molecule in that water is constantly jostling its neighbours. They collide, change direction, and bounce apart again, millions of times every second. If the water is cold, the molecules move relatively slowly. If the water is heated, they move more quickly and collide with greater energy. Continue heating the water, and eventually those molecules move fast enough to escape from the liquid entirely. That is when water begins to boil and turn into steam. The same basic principle applies to almost everything in the universe. Temperature is simply a measure of how energetic particles are within a system. This understanding led scientists to develop a precise language for describing heat. One important distinction is the difference between heat and temperature. In everyday conversation, the two words often mean the same thing, but in physics they represent different ideas. Temperature describes how energetic the particles are on average. Heat refers to energy being transferred from one object to another because of a temperature difference. If you place a warm cup of tea on a cool table, energy flows from the tea into the surrounding air and into the table itself. That transfer of energy is heat. The tea's temperature slowly drops as the particles inside lose energy. Meanwhile, the surrounding environment warms slightly. This exchange continues until everything reaches the same temperature. At that point, the system is said to be in thermal equilibrium. This concept appears everywhere in nature. Objects that come into contact gradually share energy until their temperatures balance out. It is the same reason ice melts when dropped into warm water. Energy moves from the warmer liquid into the colder ice, causing the solid structure of ice crystals to break apart. In the process, the water cools and the ice warms until both reach the same temperature. Understanding this energy transfer allowed scientists to develop thermodynamics, the branch of physics that studies heat and energy. Thermodynamics explains not only how temperature works, but also how energy flows through engines, weather systems, stars, and even living organisms. One of the most useful ideas in thermodynamics is the concept of absolute zero. Absolute zero represents the lowest possible temperature in the universe. It occurs when particles contain the smallest amount of motion physically allowed. On the Celsius scale, absolute zero is negative 273 degrees. On the Kelvin scale, which scientists often use in physics, absolute zero is defined as 0 Kelvin. The Kelvin scale is convenient because it begins at the lowest possible temperature. There are no negative numbers. Every temperature represents a specific amount of particle motion above absolute zero. For example, room temperature is roughly 293 Kelvin. The surface of the Sun is around 5,800 Kelvin. And many of the hottest phenomena in the universe reach temperatures of billions or even trillions of Kelvin. When temperatures reach those levels, matter behaves in ways that seem almost impossible compared with everyday experience. Atoms themselves can no longer remain intact. Electrons break free from atomic nuclei, creating plasma, a state of matter where charged particles move freely in an energetic mixture. Plasma is actually the most common state of matter in the universe. Stars are made of plasma. Lightning is a brief flash of plasma. Even glowing auroras in the polar skies are caused by energetic plasma interacting with Earth's atmosphere. Yet despite its abundance across the cosmos, plasma rarely appears in everyday life on Earth. Most objects around us exist as solids, liquids or gases because temperatures here are relatively moderate. To reach the conditions where plasma dominates, enormous amounts of energy are required. And that leads to an interesting realization. The hottest places in the universe are not simply places with fire or glowing surfaces. They are places where energy is concentrated to such extremes that matter itself begins to break apart. Another useful way to understand temperature is through the idea of kinetic energy. Kinetic energy is the energy of motion. If you throw a ball, the ball carries kinetic energy because it is moving. When the ball hits something and stops, that energy transfers into the object it strikes or into the surrounding environment. Particles inside matter behave in a similar way, although on a much smaller scale. Atoms and molecules vibrate, spin, and collide with one another. Each motion carries kinetic energy. Temperature represents the average kinetic energy of those particles. When energy is added to a system, particle motion increases. When energy is removed, motion decreases. This connection between motion and temperature allows scientists to calculate temperature even in environments where traditional thermometers would never survive. Astronomers, for example, can estimate the temperature of distant stars by analysing the light they emit. Hot objects tend to glow with specific colours depending on their temperature. A relatively cool star may appear red or orange. A hotter star glows white. The hottest stars shine blue. This colour pattern occurs because atoms in hot environments emit radiation at different wavelengths depending on how energetic they are. By studying those wavelengths, astronomers can estimate stellar temperatures even across vast distances. Another method involves studying the behaviour of particles in extreme environments. For instance, when gas spirals toward a black hole, it accelerates to enormous speeds. Friction and gravitational compression heat the gas dramatically. The resulting radiation carries information about temperature. Observations of this radiation allow scientists to estimate just how hot the gas becomes as it falls toward the black hole. In some cases, the temperatures involved reach tens of millions of degrees. Even those numbers, impressive as they sound, are still far below the most extreme temperatures ever observed. There is also a fascinating relationship between temperature and energy density. Energy density refers to how much energy exists within a given amount of space. When enormous amounts of energy are squeezed in tiny volumes, temperatures rise dramatically. This principle explains why events like supernova explosions can reach extraordinary temperatures. When a massive star collapses under its own gravity, enormous energy becomes concentrated in a small region. The sudden compression causes matter to heat intensely before the star explodes outward. During those moments, temperatures can climb into the billions of degrees, but the scale of heat in the universe does not stop there. Particle physics experiments on Earth have produced even higher temperatures, briefly recreating conditions similar to those that existed just after the Big Bang. Inside enormous particle accelerators, atoms are smashed together at incredible speeds. These collisions release vast amounts of energy in tiny spaces, heating the resulting particles to trillions of degrees. Such temperatures exist for only fractions of a second, but they reveal something remarkable about the nature of matter. Under those conditions, even protons and neutrons begin to break apart into their fundamental components. the universe briefly returns to a state similar to the one it experienced in its earliest moments. Understanding temperature in this way also helps scientists compare vastly different environments. The core of the Sun might reach 15 million degrees. A supernova explosion may reach billions. Particle collisions in laboratories can exceed several trillion degrees. And theoretical models suggest that the earliest fractions of a second after the Big Bang were hotter still. At that time, temperatures were so extreme that the laws of physics themselves behaved differently from the way we observe them today. But before considering those early moments of the universe, there is another important question to explore. If heat is simply energy moving between objects, how do scientists measure temperatures in places that are unimaginably far away? After all, no one can travel to the surface of a distant star with a thermometer in hand. Astronomers rely on careful observation and clever techniques to estimate temperatures across space. By studying light, radiation, and particle behavior, they can determine how energetic distant environments must be. This process allows scientists to map temperatures throughout galaxies, star systems, and interstellar clouds. Through these methods, researchers have gradually identified some of the most extreme thermal environments in existence. But measuring those temperatures requires tools far more sophisticated than the simple thermometers once used to study everyday weather. Understanding temperature becomes much more complicated once we move beyond everyday objects. A thermometer works perfectly well for measuring the warmth of the air in your room or the temperature of water on a stove. But the universe is filled with environments where no instrument could survive long enough to take a reading. The surface of a star would melt any probe instantly. The gas spiraling around a black hole would tear apart most materials long before they could measure anything. So scientists had to find another way. Instead of touching these environments directly, they learned to read the signals that hot matter naturally sends into space. Heat does not remain hidden. Whenever particles move with enough energy, they release radiation. That radiation travels outward in the form of light or other electromagnetic waves, carrying information about the conditions where it was produced. In other words, hot objects announce their temperature through the energy they emit. This idea is one of the most powerful tools in astronomy. By observing the light from distant objects, scientists can estimate temperatures across the universe without ever traveling to those places. The method works because of a simple relationship between heat and radiation. Any object with a temperature above absolute zero emits electromagnetic radiation. The amount and type of radiation depend on how energetic the particles inside that object are. Warmer objects release radiation with shorter wavelengths and higher energy. Cooler objects emit longer wavelengths with less energy. You experience a small part of this effect every day. If you place your hand near a warm surface without touching it, you can sometimes feel heat radiating toward your skin. That sensation comes from infrared radiation, a form of light that our eyes cannot see but our bodies can detect as warmth. Many animals can sense infrared radiation even more effectively than humans. Some snakes, for example, use specialized heat-sensitive organs to locate warm-blooded prey in the dark. The prey does not glow visibly, but its body temperature produces infrared radiation that the snake can detect. Scientists have developed instruments that work on a similar principle. Infrared cameras allow us to visualize heat differences in everyday environments. Buildings, engines, animals, and even human bodies appear as glowing patterns when viewed through these devices. Warmer areas emit stronger infrared signals and appear brighter in the image. Now imagine applying that idea to the entire universe. Astronomers use telescopes designed to detect different kinds of radiation, including infrared, visible light, ultraviolet radiation, X-rays, and gamma rays. Each type of radiation corresponds to different energy levels and therefore different temperature ranges. Cooler objects in space often emit mostly infrared radiation. Dust clouds between stars, for example, may be extremely cold by human standards, sometimes only a few dozen degrees above absolute zero. These clouds glow faintly in infrared wavelengths, allowing astronomers to map their structure even though they appear completely dark to visible light telescopes. Hotter objects emit radiation at shorter wavelengths. Stars like our Sun radiate strongly in visible light because their surfaces are thousands of degrees hot. Extremely hot environments such as supernova remnants or gas falling into black holes can emit intense X-rays or even gamma rays. Those forms of radiation are so energetic that they cannot pass through Earth's atmosphere easily, which is why many telescopes designed to observe them must operate in space. By studying the wavelengths and intensity of radiation coming from an object, scientists can estimate its temperature. The process involves analysing what is called a spectrum. When light from a star or other object is spread out into its component wavelengths, it forms a spectrum, similar to how sunlight passing through a prism produces a rainbow. Each colour or wavelength carries information about the physical conditions of the source. Some parts of the spectrum appear brighter than others. Certain wavelengths may be missing entirely. These patterns reveal details about the temperature, chemical composition, and motion of the object emitting the light. Hotter objects tend to produce spectra that peak at shorter wavelengths. Cooler ones peak at longer wavelengths. By identifying where that peak occurs, astronomers can calculate an approximate temperature. This method works even across enormous distances. A star hundreds of light years away might look like a tiny point of light through a telescope, but its spectrum can still reveal whether its surface temperature is 3,000 degrees or 30,000 degrees. Another useful technique involves studying the motion of particles. In some regions of space, gas becomes so hot that its atoms and electrons move at tremendous speeds. These particles collide with each other constantly, producing radiation as they interact. By observing that radiation and understanding how fast the particles must be moving to produce it, scientists can estimate the temperature of the gas. This approach is often used when studying extremely hot environments such as supernova remnants. When a massive star explodes, its outer layers are thrown outward at incredible speeds. Shock waves travel through the surrounding gas, compressing and heating it dramatically. The resulting cloud of debris glows in X-rays because the particles inside are moving with such high energy. By measuring those X-rays, astronomers can estimate temperatures reaching millions of degrees. One particularly interesting case involves gas near black holes. As matter falls toward a black hole, it rarely plunges straight in. Instead, it forms a rotating disk around the black hole called an accretion disk. Friction between particles in the disk converts gravitational energy into heat. The gas becomes incredibly hot as it spirals inward. Temperatures in these disks can climb into the tens of millions of degrees. At those levels, the gas emits strong X-rays. Space-based observatories designed to detect X-rays allow astronomers to study these disks in remarkable detail. From Earth, the black hole itself remains invisible because not even light can escape its gravity. But the glowing disk of superheated gas surrounding it reveals that something extraordinary is happening there. Scientists also measure temperature in environments where radiation is not the only clue. In laboratories on Earth, particle accelerators allow researchers to recreate extremely energetic conditions by colliding atoms together at high speeds. When two atomic nuclei smash into each other at nearly the speed of light, the energy released in the collision briefly produces temperatures far higher than anything found in ordinary environments. Those collisions create tiny bursts of matter that behave very differently from normal atoms. For a fraction of a second, particles exist in a state known as quark-gluon plasma, where the building blocks of protons and neutrons move freely instead of remaining bound together. By studying how these particles scatter and decay, scientists can estimate the temperature of the collision. Some experiments have reached temperatures of several trillion degrees Celsius, hotter than the interior of any star. Although those conditions last for only tiny fractions of a second, they provide valuable insight into how matter behaved shortly after the universe began. There is also another remarkable way scientists detect heat across space. by observing how hot objects affect their surroundings. Hot gas expands. It pushes against nearby material and creates pressure differences that influence motion. In galaxies, clusters of galaxies, and enormous cosmic structures, astronomers can observe how hot plasma moves and interacts with gravity. For example, clusters of galaxies contain vast clouds of extremely hot gas filling the space between galaxies. This gas can reach temperatures of tens of millions of degrees. It emits X-rays that reveal the structure of the cluster and the distribution of matter within it. By mapping these X-ray emissions, scientists learn not only about temperature but also about the gravitational forces shaping the cluster. The ability to detect heat from such distant environments might seem almost magical, but it relies on careful observation combined with physical laws that apply everywhere in the universe. Radiation travels through space at the speed of the light, carrying information about its source across enormous distances. When that radiation finally reaches telescopes on Earth or in orbit, it still contains clues about the temperature and conditions where it began. This approach allows astronomers to study objects billions of light years away and still estimate their temperatures with surprising accuracy. One interesting consequence of this method is that the universe contains temperature extremes far beyond anything we experience on Earth. Cold regions of space can approach just a few degrees above absolute zero, colder than any natural environment on our planet. Meanwhile, certain cosmic events produce heat so intense that ordinary matter breaks apart completely. Understanding how to measure those extremes allows scientists to map the thermal landscape of the cosmos. Some places glow softly with faint warmth. Others blaze with radiation so energetic that it can strip atoms apart. Look up at the sky on a clear day, and the most powerful source of heat in our part of the universe is right there, shining quietly above everything else. The sun appears calm from a distance. It rises in the morning, moves slowly across the sky, and disappears below the horizon in the evening. For most of human history, it seemed like a steady lamp hanging overhead. But the calm appearance is misleading. The sun is an enormous nuclear furnace operating on a scale that is difficult to imagine. Nearly all the warmth that reaches Earth begins its journey deep inside that star. Every breeze, every ocean current, every green leaf growing towards sunlight traces its energy back to reactions happening far beneath the sun's glowing surface. To understand how hot the universe can become, it helps to begin with the nearest star we know well. The Sun sits about 150 million kilometers away from Earth. That distance might sound large, but in astronomical terms it is extremely close. Light leaving the Sun takes only about 8 minutes to reach us. If the Sun were to vanish suddenly, the sky would remain bright for 8 more minutes before darkness finally arrived. From that distance, the Sun looks like a simple glowing disk. Through telescopes, however, its surface reveals a constantly shifting landscape of bright regions, darker patches, and enormous loops of glowing gas arcing into space. All of that activity comes from the intense heat inside the star. The Sun formed roughly 4.5 billion years ago when a cloud of gas and dust collapsed under gravity. As the cloud shrank, the material at its centre became denser and hotter. Eventually the temperature rose high enough for nuclear fusion to begin. Nuclear fusion is the process that powers stars. In simple terms, fusion occurs when atomic nuclei collide with enough energy to merge together. In the Sun's core, hydrogen nuclei combine to form helium. During this process, a small amount of mass is converted directly into energy. That energy becomes the heat and light the Sun releases into space. The temperatures required for this reaction are extraordinary. At the Sun's centre, temperatures reach about 15 million degrees Celsius. At those levels, atoms no longer exist in the familiar way we encounter them on Earth. The intense heat strips electrons away from nuclei, creating a dense plasma where charged particles move freely. Inside that plasma, hydrogen nuclei move so quickly that collisions happen constantly. Most collisions simply bounce the particles apart again, but occasionally two nuclei come close enough to fuse. When that happens, energy is released and the fusion chain continues. Every second, the Sun converts around 600 million tons of hydrogen into helium. In the process, about 4 million tons of mass transform into energy, according to Einstein's famous equation, E equals mc squared. That energy begins a long journey outward. Photons created in the Sun's core do not travel straight to the surface. The interior of the Sun is extremely dense, so photons collide with particles repeatedly. Each collision sends the photon in a new direction. The path becomes a complicated random walk that can take hundreds of thousands of years before the energy finally reaches the outer layers. By the time the energy reaches the surface, it has spread through the star's enormous volume and cooled dramatically compared with the core. The surface of the Sun, known as the photosphere, has a temperature of about 5,500 degrees Celsius. That may sound modest compared with the core, but it is still hot enough to produce the bright visible light we see from Earth. The photosphere is the layer of the Sun that emits most of the light that reaches our planet. When you look at the Sun, you are seeing radiation from this glowing surface. Even this relatively thin layer is far more energetic than anything found naturally on Earth. At 5,000 degrees, matter exists as plasma rather than solid or liquid. Hydrogen atoms are partially ionized, meaning electrons are no longer tightly bound to their nuclei. The result is a churning sea of charged particles constantly interacting with intense magnetic fields. One of the most striking features visible on the Sun's surface is the presence of sunspots. Sunspots appear as dark patches scattered across the photosphere. They look dark only because they are cooler than the surrounding regions, although even the cooler temperature of a sunspot is around 4,000 degrees Celsius. These spots form when powerful magnetic fields emerging from the Sun's interior suppress the normal flow of hot material from below. Without that upward flow, the surface in that area cools slightly compared with its surroundings. Sunspots often appear in groups and can grow large enough to swallow several Earths side by side. Their presence reveals the complicated magnetic activity happening inside the star. Above the photosphere lies another layer called the chromosphere. This region glows faintly and appears reddish when viewed through specialized instruments. Temperatures there begin to rise again, climbing into the tens of thousands of degrees. Higher still is the Sun's corona, the outermost atmosphere of the star. The corona is one of the most surprising parts of the Sun. Even though it lies farther from the core where the energy originates, it is much hotter than the surface below it. Temperatures in the corona can reach 1 to 2 million degrees Celsius. This seems counterintuitive. Normally you would expect temperatures to decrease as you move away from a heat source, yet the Sun's outer atmosphere becomes hotter instead. Scientists believe this occurs because of the Sun's magnetic fields. Twisting and snapping magnetic field lines release bursts of energy that heat the surrounding plasma to extreme temperatures. The corona stretches millions of kilometers into space. During total solar eclipses, when the moon blocks the bright disk of the Sun, the corona becomes visible as a glowing halo surrounding the dark silhouette. Even though the corona is incredibly hot, it is also extremely thin. The particles there are spread far apart, so the total amount of heat you would feel within it would actually be small compared with standing near a campfire on Earth. Still, the temperature of the corona plays an important role in shaping the solar system. Particles from the corona stream outward continuously in a flow known as the solar wind. This stream of charged particles travels through space and interacts with planets, moons, and magnetic fields throughout the solar system. When the solar wind reaches Earth, our planet's magnetic field deflects most of the particles. Some, however, are guided toward the polar regions where they collide with atoms in the upper atmosphere. These collisions create the glowing curtains of light known as auroras. Auroras appear as green, red, or purple waves shimmering across the night sky. Their beauty hides the energetic interactions between solar particles and Earth's atmosphere. the Sun occasionally produces more dramatic bursts of energy. Solar flares occur when magnetic fields near sunspots suddenly release enormous amounts of stored energy. During a flare, radiation across the electromagnetic spectrum surges outward. Some flares are accompanied by coronal mass ejections, giant clouds of plasma hurled into space. These events can accelerate particles to extremely high speeds and raise local temperatures to tens of millions of degrees. If directed toward Earth, such eruptions can interfere with satellites, radio communications, and electrical systems. Fortunately, our planet's magnetic field shields us from most of their direct effects. Despite its enormous energy output, the Sun is actually considered an average star. There are many stars in the galaxy that are hotter, larger, and more energetic. Some burn through their nuclear fuel much more quickly than the Sun, producing far greater heat and brightness. The Sun's relative stability is one of the reasons life has been able to develop on Earth. Stars far more massive than the Sun tend to live shorter, more violent lives. Their cores burn hotter and faster, leading eventually to explosive endings that scatter heavy elements across space. Those elements later become the building blocks of planets, oceans, and living organisms. In that sense, even the heat of the Sun is part of a much larger cosmic cycle. Energy produced in stellar cores spreads across galaxies, shaping the environments where new stars and planets eventually form. The Sun may feel unimaginably hot compared with anything on Earth, but it represents only a middle step in the scale of cosmic temperatures. Its surface reaches thousands of degrees. Its core reaches millions. If the Sun already seems unimaginably hot, it may come as a surprise that many stars burn at temperatures far beyond it. Our star feels intense because it is the closest one we know, yet across the galaxy there are stars whose surfaces are several times hotter, and whose energy output dwarfs anything happening in our solar system. The Sun belongs to a category astronomers call a yellow dwarf. The name might sound modest, but it simply refers to a star of moderate size and temperature. On the stellar scale, yellow dwarfs sit somewhere in the middle. They are hotter than small red stars but cooler than the most massive blue ones. When astronomers classify stars, temperature plays a central role. Stars are grouped into spectral classes based largely on how hot their surfaces are and what kinds of light they emit. These categories run from the coolest stars, which glow faintly red, all the way up to the hottest stars that shine with brilliant blue light. Red stars, often called red dwarfs, have surface temperatures of roughly 3,000 degrees Celsius. They burn slowly and steadily, using their fuel at a relaxed pace. Some of these stars may live for hundreds of billions of years, far longer than the current age of the universe. Our Sun, at around 5,500 degrees Celsius on its surface, falls into a warmer category. But above that range are stars whose temperatures rise dramatically. White stars can reach around 10,000 degrees Celsius. Their intense brightness makes them easy to spot even across large distances. And then there are the blue stars. These are among the hottest normal stars in the universe. Their surfaces can reach temperatures of 20,000, 30,000, or even 40,000 degrees Celsius. At those temperatures, the radiation they emit shifts toward the blue and ultraviolet part of the spectrum. Blue stars shine with a dazzling brightness that can outshine the Sun tens of thousands of times over. The reason these stars burn so hot comes down to mass. Massive stars experience much stronger gravitational forces at their cores. That gravity squeezes the stellar material with enormous pressure, raising temperatures high enough for nuclear fusion to proceed much faster than it does in smaller stars. In a star like the Sun, hydrogen fusion occurs at a steady pace. The energy released balances gravity, keeping the star stable for billions of years. In massive stars, however, the stronger gravity pushes the core temperature much higher. Nuclear reactions accelerate dramatically. The star releases energy at a much greater rate, causing it to glow brighter and hotter. But there is a trade-off. Stars that burn hotter also consume their fuel far more quickly. A star several times the mass of the Sun might shine with thousands of times the brightness, yet it may live only a few million years before exhausting its core fuel. In cosmic terms, that is an extremely short lifespan. One famous example of a massive blue star is Rigel, located in the constellation Orion. Rigel shines with a brilliant blue-white colour visible even to the naked eye from Earth. Its surface temperature is roughly 12,000 degrees Celsius, more than twice that of the Sun's surface. Despite being hundreds of light years away, Rigel appears bright in the night sky because it releases an enormous amount of energy. Stars even hotter than Rigel exist in the upper ranges of the stellar classification system. Some of the hottest stars are known as O-type stars. Their surfaces can exceed 40,000 degrees Celsius. These stars are rare but incredibly powerful. Their intense radiation can strip electrons from nearby atoms, creating large glowing regions of ionized gas in surrounding space. These regions, known as emission nebulae, often appear as colourful clouds in astronomical images. The heat and radiation from nearby massive stars energize the gas within the nebula, causing it to glow. In many ways, these hot stars act like cosmic engines shaping their environments. The strong radiation they emit pushes away surrounding gas and dust. Their stellar winds, streams of charged particles flowing outward from their surfaces, can reach speeds of thousands of kilometers per second. Over time, these winds carve cavities in nearby clouds of interstellar material. Within those clouds, new stars are forming. The intense heat from massive stars influences that process. Sometimes the radiation compresses nearby gas, triggering the birth of new stars. In other cases, the energy disperses the cloud entirely, halting star formation. These interactions reveal that stellar heat is not simply a local phenomenon confined to the star itself. It shapes entire regions of space. Yet even the hottest blue stars are only part of the story. As massive stars evolve, their temperatures can change dramatically. After burning hydrogen in their cores, some stars expand into enormous red supergiants. Despite their reddish colour suggesting cooler surfaces, these stars can reach sizes hundreds of times larger than the Sun. Others follow different evolutionary paths and become even hotter in later stages. One striking example involves a type of star known as a Wolf-Rayet star. Wolf-Rayet stars are among the most extreme stellar objects known. They represent a late stage in the life of very massive stars. During this phase, powerful stellar winds blow away the outer layers of the star, exposing deeper, hotter regions beneath. The exposed surface of a Wolf-Rayet star can reach temperatures well above 100,000 degrees Celsius. At those temperatures, the star emits intense ultraviolet radiation and powerful stellar winds that carry material into space at astonishing speeds. These winds can shape surrounding nebulae into complex structures of glowing gas. Some Wolf-Rayet stars lose mass so rapidly that they shed enormous amounts of material over relatively short periods of time. The ejected gas forms expanding shells around the star, illuminated by the fierce radiation coming from its surface. Eventually, many of these massive stars reach a dramatic conclusion. When the nuclear fuel in the core can no longer support the star against gravity, the core collapses. In the moments before and during that collapse, temperatures rise to extraordinary levels. The resulting explosion, known as a supernova, releases more energy in a few seconds than the Sun will produce in its entire lifetime. During such events, temperatures can soar into the billions of degrees. But that stage belongs to a later part of the story. Before reaching the violent end of massive stars, there are still many remarkable details about how stellar heat operates within the stars themselves. Inside a star, heat does not simply remain in one place. Energy generated in the core must move outward through the surrounding layers. In the Sun, this happens through a combination of radiation and convection. Radiation transports energy as photons slowly scatter through the dense plasma. Convection occurs when hot material rises toward the surface, while cooler material sinks downward, creating enormous circulating currents. In larger stars, these processes can behave differently, so massive stars mix their interior material much more efficiently, allowing fresh hydrogen to reach the core while heavier elements move outward. This mixing affects how long the star can continue burning fuel and how its temperature evolves over time. Astronomers study these processes carefully because they reveal how stars live and die. Understanding stellar temperatures also helps scientists interpret the light from distant galaxies. When astronomers observe the combined glow of billions of stars in another galaxy, they can analyze the spectrum of that light to determine the types of stars present. If the galaxy's light contains strong ultraviolet radiation, it suggests the presence of hot, massive stars. If the light appears redder, it may indicate an older population of cooler stars. Through these observations, scientists can estimate the age, composition, and history of distant galaxies. In that way, the heat of stars becomes a tool for understanding the structure of the universe itself. Despite their incredible temperatures, however, even the hottest stars represent only part of the thermal extremes that exist in space. Stars generate enormous heat through nuclear fusion, but certain cosmic events push temperatures even higher. For most of its life, a star maintains a delicate balance. Gravity pulls inward, trying to compress the star's enormous mass into a smaller and smaller space. At the same time, nuclear fusion in the core releases energy that pushes outward. As long as those two forces remain balanced, the star remains stable. It shines steadily, releasing light and heat across space. But that balance cannot last forever. Eventually, the fuel that powers the star begins to run out. In stars like the Sun, this transition happens slowly. Billions of years from now, the Sun will expand into a red giant and later shed its outer layers, leaving behind a quiet remnant called a white dwarf. Massive stars follow a much more dramatic path. When a star several times more massive than the Sun approaches the end of its life, the nuclear reactions in its core change in a rapid sequence. The star begins fusing heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen and neon. Each new stage of fusion requires higher temperatures and pressures than the last. As the core contracts under gravity, temperatures rise to keep the fusion reactions going. For a time, the star manages to support itself this way, but each stage of fusion lasts for a shorter period than the previous one. Hydrogen burning might last millions of years. Helium burning may last hundreds of thousands. Later reactions involving heavier elements may last only years, days, or even hours. Eventually, the star begins producing iron in its core. Iron marks the turning point. Unlike lighter elements, fusing iron does not release energy. Instead, it consumes energy. Once iron accumulates in the core, the star can no longer produce the outward pressure needed to resist gravity. At that moment, the balance that supported the star for millions of years collapses. Gravity suddenly takes over. The core begins to fall inward with incredible speed. Matter that once moved slowly through the stellar interior now accelerates toward the center at thousands of kilometers per second. As the core collapses, the density and temperature rise dramatically. Electrons are forced into atomic nuclei, combining with protons to form neutrons. The collapsing material compresses into an incredibly dense ball only a few tens of kilometers across. When the collapse finally stops, the core rebounds violently. The outer layers of the star, still rushing inward, slam into this suddenly rigid core. The impact creates an enormous shock wave that blasts outward through the star. This is the beginning of a supernova. The shock wave tears through the star's interior, heating the surrounding material to extraordinary temperatures. Nuclear reactions occur rapidly as the shock wave passes through each layer of the star. Elements heavier than iron are formed during these moments. Gold, uranium, and many other rare elements in the universe are created during supernova explosions. The intense heat and pressure allow atomic nuclei to capture particles and form new elements that would never appear in normal stellar fusion. Meanwhile, the star itself is being torn apart. The shock wave reaches the surface and ejects the star's outer layers into space at enormous speeds. For a brief time, the exploding star may shine as brightly as an entire galaxy. From Earth, supernovae appear as sudden new stars that brighten dramatically before fading away over weeks or months. Historically, several of these explosions have been visible to the naked eye. In the year 1054, observers in China and the Middle East recorded the appearance of a bright new star in the sky. For several weeks, it was visible even during daylight. Today we know that event as the supernova that created the Crab Nebula. The expanding cloud of gas from that explosion is still visible through telescopes nearly 1,000 years later. At its centre lies a neutron star, the collapsed core of the original star. During the explosion itself, temperatures reach astonishing levels. As the core collapses and the shockwave forms, temperatures climb to billions of degrees Celsius. These extreme conditions exist for only a short time, but they represent some of the hottest environments that occur naturally in the universe. Particles inside the exploding star move with tremendous energy. Atoms are stripped apart completely, and nuclear reactions occur in rapid chains. Radiation pours outward across the electromagnetic spectrum, from visible light to X-rays and gamma rays. The surrounding space becomes flooded with energy. Even after the initial explosion fades, the expanding debris cloud remains extremely hot. Shockwaves continue to heat the surrounding gas as the material plows through interstellar space. Astronomers often observe supernova remnants using X-ray telescopes. These instruments reveal clouds of plasma heated to millions of degrees as the shock waves interact with nearby gas. Over time, the expanding debris spreads out across light years of space. Eventually it cools and mixes with surrounding interstellar material. Those enriched clouds of gas later become the birthplace of new stars and planets. The iron in your blood, the calcium in your bones, and many of the heavier elements around you were once forged in the heart of a dying star. Long before the solar system formed, ancient supernova scattered those elements across space. Our planet formed from material that had already passed through multiple generations of stars. Supernova explosions come in more than one form. The type described earlier occurs when a massive star collapses under its own gravity. Astronomers call this a core collapse supernova. Another type occurs in binary star systems involving white dwarfs. White dwarfs are dense stellar remnants left behind when smaller stars exhaust their nuclear fuel. These objects pack a mass comparable to the Sun into a volume roughly the size of Earth. In certain binary systems, a white dwarf orbits a companion star. If the two stars are close enough, the white dwarf can begin pulling gas from its companion. The stolen gas accumulates on the white dwarf's surface, slowly increasing its mass. There is a limit to how massive a white dwarf can become while remaining stable. This threshold is known as the Chandrasekhar limit. If the white dwarf's mass approaches this limit, the pressure inside becomes great enough to ignite runaway nuclear fusion. Unlike the steady fusion inside normal stars, this reaction spreads explosively through the entire white dwarf. Within seconds, the star is completely destroyed. This event produces a Type 1a supernova. The explosion releases enormous energy and briefly heats the stellar material to extremely high temperatures. Like core collapse supernovae, these explosions scatter heavy elements across space and produce expanding clouds of glowing gas. Astronomers study Type 1a supernovae carefully because their brightness follows predictable patterns. By measuring how bright these explosions appear from Earth, scientists can estimate distances across the universe. These observations played an important role in discovering that the expansion of the universe is accelerating. Even though supernova explosions are brief compared with the lifetime of stars, they represent some of the most violent and energetic events in the cosmos. The temperatures involved push matter into extreme states. At billions of degrees, atomic structure breaks down entirely. Nuclei collide with enormous energy, creating new elements and releasing powerful radiation. When a massive star reaches the end of its life and explodes as a supernova, the explosion scatters most of the star's material across space. Yet not everything escapes. Deep in the centre, the collapsing core of the star can remain behind as a compact remnant so dense and unusual that it behaves unlike any familiar object in everyday life. This remnant is known as a neutron star. Despite the name, a neutron star is not a typical star anymore. It no longer produces energy through nuclear fusion like the Sun does. Instead, it is the compressed core of a once massive star, a leftover object formed when gravity squeezed matter to extraordinary densities. To picture what that means, it helps to consider how extreme the collapse becomes. During the final moments before the supernova explosion, the core of the star shrinks dramatically. A region that once spanned thousands of kilometers collapses into an object only about 20 kilometers across. That is roughly the size of a city. Yet the mass of the core remains enormous. A typical neutron star may contain more mass than the Sun. That means an amount of matter comparable to the entire solar system's central star has been squeezed into a sphere no larger than a small metropolitan area. The resulting density is almost impossible to imagine. If you could scoop up a teaspoon of neutron star material and somehow bring it to Earth without it exploding apart, that tiny amount would weigh billions of tons. The matter inside neutron stars is compressed so tightly that the usual structure of atoms can no longer exist. Under these conditions, electrons are forced into atomic nuclei, combining with protons to form neutrons. The star becomes essentially a giant ball of neutrons packed together in an extremely dense arrangement. That is where the name comes from. But density is only part of the story. When a neutron star first forms in the aftermath of a supernova, it is incredibly hot. The collapse that created it released enormous gravitational energy. Much of that energy heated the newly formed neutron star to extraordinary temperatures. In the moments immediately after formation, temperatures in the interior can reach around 100 billion degrees Celsius. That is far hotter than the core of any ordinary star. At those temperatures, the matter inside the neutron star exists in a state far beyond the familiar forms of solid, liquid, or gas. Even plasma, which dominates the interiors of stars like the Sun, does not fully describe the behavior of matter under such extreme compression and heat. Physicists are still working to understand exactly how particles behave inside neutron stars. Some theories suggest that the neutrons themselves may break apart into their fundamental components, forming an exotic mixture of particles sometimes referred to as quark matter. Whether this occurs depends on conditions that remain difficult to study directly. What scientists do know is that neutron stars cool over time. After the supernova explosion fades, the newborn neutron star begins radiating energy into space. The outer layers cool gradually, dropping from billions of degrees to millions over the course of thousands or millions of years. Even after this cooling period, however, neutron stars remain extremely hot by human standards. The surface temperature of a young neutron star may still reach several million degrees Celsius. At those temperatures, the star emits powerful X-rays that can be detected by space telescopes. Astronomers observe these X-rays to study neutron stars across the galaxy. Because neutron stars are so small and distant, they usually appear as faint points of light even in powerful telescopes. But their radiation carries information about their temperature, magnetic fields, and rotation. Rotation is another remarkable feature of these objects. When the core of a star collapses into a neutron star, its rotation speeds up dramatically. This happens for the same reason an ice skater spins faster when pulling their arms inward. As the collapsing star shrinks to a tiny fraction of its original size, its rotation rate increases. Some neutron stars spin dozens or even hundreds of times per second. This rapid rotation, combined with extremely strong magnetic fields, creates one of the most fascinating phenomena in astrophysics: pulsars. A pulsar is a rotating neutron star that emits beams of radiation from its magnetic poles. These beams sweep across space as the star spins. If one of those beams crosses Earth, astronomers observe a regular pulse of radiation each time the beam passes our line of sight. The pulses can be astonishingly precise. Some pulsars rotate hundreds of times per second, producing pulses as regular as the ticking of a clock. In fact, certain pulsars are so stable that they rival the accuracy of atomic clocks on Earth. The radiation emitted by pulsars often includes X-rays and gamma rays, indicating extremely energetic processes near the star's surface. Part of this energy comes from the star's powerful magnetic field. Neutron stars possess the strongest magnetic fields known in the universe outside of black holes. These fields can be trillions of times stronger than Earth's magnetic field. Such intense magnetism affects the behavior of charged particles around the star. Particles trapped by the magnetic field accelerate along field lines at incredible speeds. As they move, they emit radiation across a wide range of wavelengths. The resulting glow reveals how energetic the environment near the neutron star can be. In some cases, neutron stars become even more extreme. A special category known as magnetars possesses magnetic fields thousands of times stronger than ordinary neutron stars. The magnetic energy stored in these fields can twist and fracture the crust of the star itself. When that happens, enormous bursts of energy are released. These events, known as starquakes, can produce intense flashes of gamma rays detectable across large distances in the galaxy. During such outbursts, temperatures near the star's surface may briefly climb to extraordinary levels as energy spreads through the surrounding plasma. Even though neutron stars are tiny compared with ordinary stars, their influence can extend far into space. Some neutron stars exist in binary systems, orbiting close to another star. If the neutron star's gravity begins pulling gas from its companion, the stolen material forms a swirling disk around the neutron star. This situation resembles the accretion disks found around black holes, though the physical processes differ slightly. As gas spirals inward toward the neutron star, friction heats the material dramatically. Temperatures in the accretion disk can climb into the tens of millions of degrees. The hot plasma emits X-rays that astronomers detect using specialized space telescopes. These X-ray binaries provide important clues about how matter behaves under extreme gravity and temperature. Occasionally, the accumulated gas on the neutron star's surface ignites in sudden bursts of nuclear fusion. These events, known as X-ray bursts, release tremendous energy in a matter of seconds. During the burst, temperatures can briefly rise to billions of degrees before settling back down. Such bursts demonstrate that even long after their violent birth, neutron stars can still produce moments of extraordinary heat. Yet despite their extreme temperatures and dense structure, neutron stars are not the final stage of stellar collapse. Neutron stars already represent some of the most extreme objects in the universe. Their density is staggering, their magnetic fields are immense, and the heat they produce during their formation reaches extraordinary levels. Yet there exists another kind of cosmic object where matter can experience even more intense conditions. That object is a black hole. The name black hole can make it sound like a simple empty space, as though it were merely a hole punched into the fabric of the universe. In reality, a black hole is anything but empty. It's a region where gravity has become so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Black holes form when extremely massive stars collapse at the end of their lives. If the collapsing core contains enough mass, gravity overwhelms every force that might resist it. Instead of stabilizing as a neutron star, the matter continues compressing until it becomes a black hole. The event horizon marks the point where escape becomes impossible. Anything that crosses this boundary can never return to the outside universe. Despite this dramatic description, black holes themselves do not glow. If a black hole existed entirely alone in empty space, it would be invisible. There would be nothing to reveal its presence except its gravitational influence on nearby objects. But most black holes are not completely isolated. In many parts of the universe, black holes are surrounded by gas, dust, or even entire stars. When matter begins falling toward a black hole, something remarkable happens. The material does not plunge directly inward all at once. Instead, it begins to spiral. As gas approaches a black hole, it forms a rotating structure known as an accretion disk. This disk is made of material gradually moving inward, orbiting the black hole while losing energy through friction and collisions between particles. The word disk might suggest something thin and quiet, but in reality these structures are among the most violent environments in the universe. The gas within an accretion disk moves at incredible speeds. Near the inner regions of the disk, matter may orbit the black hole at a significant fraction of the speed of light. As particles race around the disk, they collide constantly with neighbouring particles. Each collision converts some of the particles' motion into heat. With trillions of collisions happening every second, the temperature of the disk rises rapidly. The result is one of the hottest naturally occurring environments known in the cosmos. Temperatures in the inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees Celsius. At these temperatures, the gas becomes an extremely energetic plasma that emits powerful X-rays. Astronomers detect these X-rays using space telescopes designed specifically for that purpose. Observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton telescope allow scientists to study the glowing disks surrounding black holes across our galaxy. The X-ray radiation produced by accretion disks reveals how matter behaves as it approaches the most extreme gravitational environments. In some systems, the black hole is part of a binary pair with an ordinary star. Over time, the black hole's gravity can pull gas away from its companion. This stolen gas forms the accretion disk, gradually spiraling inward toward the event horizon. These systems are known as X-ray binaries because the heated gas in the disk emits strong X-ray radiation. From Earth, the black hole itself remains invisible, but the glowing disk surrounding it reveals the intense activity taking place there. The closer gas gets to the black hole, the faster it moves and the hotter it becomes. Near the inner edge of the disk, the particles are so energetic that the plasma radiates enormous amounts of energy into space. The heat generated in these regions can rival the temperatures found in the cores of stars. In fact, the energy output of an accretion disk can sometimes exceed the energy produced by nuclear fusion in a star of similar mass. Gravity alone powers this process. As matter falls deeper into the black hole's gravitational well, gravitational potential energy is converted into heat and radiation. The closer the material moves toward the event horizon, the more energy is released. This process can be remarkably efficient. In some cases, the conversion of gravitational energy into radiation around black holes releases more energy per unit of mass than nuclear fusion itself. But stellar mass black holes are only part of the story. At the centres of most galaxies, including our own Milky Way, there exist black holes millions or even billions of times more massive than the Sun. These are called supermassive black holes. When large amounts of gas fall toward a supermassive black hole, the resulting accretion disk becomes truly enormous. The disk may stretch across distances comparable to the size of the solar system, or even larger. Temperatures within these disks can vary dramatically depending on the distance from the black hole. Outer regions of the disk may glow in visible light, while the inner regions become hot enough to emit ultraviolet radiation and powerful X-rays. The combined radiation from these disks can make the centres of galaxies shine with incredible brightness. Some of the brightest objects in the universe are powered by supermassive black holes consuming surrounding material. These objects are known as quasars. Quasars appear as brilliant points of light visible across billions of light-years of space. Despite their small appearance in telescopes, they release enormous amounts of energy. In fact, a single quasar can outshine the combined light of all the stars in the galaxy that contains it. The heat generated within the accretion disk of a quasar reaches extraordinary levels. Gas spiraling into the central black hole becomes so energetic that it produces intense radiation across the electromagnetic spectrum. The disk glows with extreme brightness as matter races inward at tremendous speeds. In addition to the disk itself, some black hole systems produce enormous jets of energy. Magnetic fields within the accretion disk can channel some of the surrounding plasma into narrow beams that shoot outward along the black hole's rotational axis. These jets travel vast distances into space, sometimes extending far beyond the boundaries of the host galaxy. Particles inside these jets move close to the speed of light. Although the jets themselves are not necessarily the hottest regions near the black hole, they represent another example of how energy released by accretion disks can influence enormous regions of space. Astronomers continue studying accretion disks to understand how matter behaves under such extreme conditions. The physics involved include strong gravity, high temperatures, intense magnetic fields, and relativistic effects predicted by Einstein's theory of general relativity. All of these factors combine to create environments unlike anything found elsewhere in the universe. Yet even though accretion disks are extraordinarily hot, they are still not the hottest conditions that have ever existed. Not long after astronomers began studying the universe with radio telescopes in the 20th century, they noticed something puzzling. Some objects in the sky appeared almost like ordinary stars through optical telescopes, just tiny points of light. Yet when scientists examined their radio signals and spectra, those points behaved nothing like normal stars. The radiation coming from them was far too powerful. These objects were eventually given the name quasars, short for quasi-stellar radio sources. The name reflects the way they first appeared, star-like in telescopes, but clearly something much more energetic. As astronomers studied quasars more carefully, the scale of what they were observing became clear. Quasars are not stars at all. They are the incredibly bright centers of distant galaxies, powered by supermassive black holes consuming enormous amounts of matter. The heat and radiation produced in those regions make quasars some of the most luminous objects ever observed. To understand why quasars become so bright and hot, imagine what happens when vast clouds of gas fall toward a supermassive black hole. Earlier, we explored how accretion disks form when material spirals inward. In quasars, this process occurs on a much larger scale. The central black hole may contain millions or even billions of times the mass of the Sun. The surrounding disk of gas stretches across distances comparable to the entire solar system or larger. Gas drawn toward the black hole does not fall quietly. It collides, compresses, and accelerates as gravity pulls it closer to the center. Friction between particles converts enormous amounts of gravitational energy into heat. The disk grows hotter and hotter as the material spirals inward. The temperatures reached in these regions are extraordinary. Outer portions of the disk may glow with temperatures of several thousand degrees, producing visible light similar to that emitted by stars. Moving closer toward the black hole, temperatures rise dramatically. Inner regions of the disk can reach tens of millions of degrees Celsius. At those temperatures, matter becomes an extremely energetic plasma that emits intense ultraviolet radiation and X-rays. The radiation pouring out of a quasar can be so powerful that it illuminates gas across the entire host galaxy. Even from billions of light years away, quasars can appear brighter than many closer galaxies. When astronomers first realized how distant quasars were, the discovery was astonishing. Objects that appeared faint in telescopes turned out to be unimaginably far away. Their brightness implied that they were releasing more energy than entire galaxies filled with billions of stars. At first, scientists struggled to explain how anything could generate that much energy. The solution became clearer once astronomers understood the role of supermassive black holes. As matter falls into a black hole's accretion disk, the conversion of gravitational energy into radiation can be extremely efficient. In fact, this process can release more energy per kilogram of material than nuclear fusion inside stars. The energy comes from the gravitational potential of matter falling into a deep gravitational well. As particles spiral inward, They lose energy through friction and collisions. That energy escapes in the form of heat and radiation. A quasar can shine with the brightness of trillions of suns. Despite that enormous output, the actual region producing the radiation is relatively small compared with the size of the galaxy surrounding it. Most of the visible light comes from the accretion disk itself, where temperatures are highest. Astronomers studying quasars often examine their spectra, the spread of light across different wavelengths. These spectra reveal information about the temperature and motion of gas near the black hole. Some spectral lines appear broadened or shifted because the gas in the disk is moving extremely fast. The inner regions of the disk may orbit the black hole at significant fractions of the speed of light. When gas moves that quickly, the light it emits is affected by relativistic effects predicted by Einstein's theory of relativity. Astronomers can analyze these changes to estimate how close the gas lies to the event horizon. Another fascinating feature of quasars involves the enormous jets that sometimes emerge from the central region. Magnetic fields surrounding the black hole and its accretion disk can channel some of the plasma into narrow beams that shoot outward along the rotational axis. These jets travel far beyond the central galaxy, sometimes extending for hundreds of thousands of light years. Particles within these jets move at speeds approaching the speed of light. Although the jets themselves are not necessarily the hottest regions, they carry enormous amounts of energy away from the central engine. As the particles travel outward, they interact with surrounding gas and magnetic fields, producing radio waves, X-rays, and sometimes gamma rays. Observing these jets helps astronomers understand how energy from the black hole influences the surrounding galaxy. Quasars also play an important role in the history of the universe. Many of the brightest quasars are observed at extremely large distances, meaning their light has been travelling toward Earth for billions of years. When astronomers observe those objects, they are seeing them as they existed in the early universe. During that time, galaxies were still forming and growing. Supermassive black holes in young galaxies often had abundant gas falling toward them. As a result, quasar activity was much more common in the early universe than it is today. Over time, many galaxies consumed or expelled much of the gas near their centres. Without that fuel, the accretion disks faded and the quasars grew quieter. Our own galaxy contains a supermassive black hole at its centre called Sagittarius A*. Compared with quasar engines, however, Sagittarius A* is relatively calm at the moment. Only small amounts of gas fall toward it, producing faint radiation compared with the brilliant output of active quasars. Yet astronomers suspect that the centre of the Milky Way may have been much more active in the distant past. Evidence suggests that bursts of energetic activity occurred long ago, possibly when larger amounts of gas were available near the central black hole. If our galaxy had experienced a full quasar phase, the centre of the Milky Way might once have shone far more brightly than it does today. Studying quasars also allows scientists to examine the material that lies between galaxies. As the intense light from a distant quasar travels across the universe, it passes through clouds of gas along the way. Each cloud absorbs specific wavelengths of light depending on its composition. When astronomers analyse the quasar's spectrum, they can see these absorption patterns and learn about the material that the light passed through on its journey. In this way, quasars act like powerful cosmic flashlights, illuminating the otherwise invisible gas scattered throughout intergalactic space. The extraordinary temperatures and energies present near quasars demonstrate just how extreme gravitational heating can become. Matter falling toward a supermassive black hole releases vast amounts of energy before crossing the event horizon. Despite the incredible heat of these environments, however, they still do not represent the most extreme temperatures that have existed in the universe. Long before stars ignited, before galaxies formed, and long before planets or oceans existed, the universe was a very different place. There were no shining suns, no drifting clouds of gas, and no quiet stretches of empty space between galaxies. In the earliest moments of cosmic history, everything that would one day become the vast universe we see today existed in a much smaller, denser, an unimaginably hotter state. If we could travel back far enough in time, the entire observable universe would appear as an intensely bright, compact region filled with energy. Temperatures were so extreme that the familiar building blocks of matter, atoms, molecules, even atomic nuclei, could not exist yet. Everything was immersed in a blazing ocean of particles and radiation. This period began with the event we call the Big Bang. The term Big Bang sometimes creates the impression of a conventional explosion, like a bomb detonating in empty space. But the reality is more subtle than that. The Big Bang was not an explosion within space. It was the expansion of space itself from an extremely dense and hot state. Every region of the universe expanded simultaneously. In those earliest moments, temperatures were extraordinarily high. Physicists estimate that immediately after the beginning, temperatures may have reached around 10 to the 32nd power Kelvin. That number is almost impossible to imagine. It is far beyond the temperatures found in stars, supernovae, or even the violent accretion disks around black holes. At such extreme temperatures, the known forces of nature behaved very differently from the way we experience them today. The familiar distinctions between particles and energy become less clear. Matter and radiation existed together in a kind of energetic mixture, where particles constantly collided, transformed, and reformed. But the earliest instant of the universe remains difficult to describe with certainty. Our current physical theories allow scientists to trace the evolution of the universe back to a fraction of a second after the beginning. Earlier than that, conditions become so extreme that the equations used in modern physics stop providing reliable answers. Researchers believe that understanding those earliest instants will require a future theory that successfully combines quantum mechanics with gravity. Even without knowing the details of the very first moment, scientists can still describe what happened soon afterward. Within the first tiny fraction of a second, the universe expanded rapidly and cooled slightly, though the temperatures remained unimaginably high. Energy dominated everything. Particles appeared and disappeared constantly through high-energy interactions. During this period, the universe was filled with fundamental particles such as quarks, gluons, electrons, neutrinos, and photons. These particles collided continuously in an environment so energetic that the usual structure of matter could not form. Quarks, which normally combine to create protons and neutrons, moved freely in a dense plasma. Gluons, the particles responsible for holding quarks together inside atomic nuclei, were also free in this energetic mixture. Physicists refer to this state as quark-gluon plasma. In this early phase, temperatures exceeded trillions of degrees. Under such conditions, particles possessed enormous kinetic energy, moving and colliding at tremendous speeds. Matter existed in a form very different from anything encountered in everyday life. As the universe continued expanding, it gradually cooled. After about 1/1,000,000th of a second, the temperature had dropped enough for quarks to begin binding together. They combined to form protons and neutrons, the particles that make up the nuclei of atoms. This transition marked an important milestone in cosmic history. For the first time, stable structures began forming within the expanding universe. The temperature at that stage was still around 1,000,000,000,000 degrees Celsius. That number may seem astonishing, but it represented a dramatic cooling compared with the earlier moments. In the rapidly expanding universe, temperature dropped as space itself grew larger. Energy spread out over an increasing volume, allowing particles to settle into more stable arrangements. Over the next few minutes, another key process took place. Protons and neutrons began combining to form the nuclei of the lightest elements. This process is known as Big Bang nucleosynthesis. During these first minutes, the universe produced the nuclei of hydrogen, helium, and small amounts of lithium. These elements would later become the building blocks of stars and galaxies. Temperatures during this stage remained extremely high, roughly billions of degrees. Nuclear reactions occurred constantly as particles collided within the dense plasma filling the universe. Eventually, as expansion continued, the universe cooled enough that nuclear reactions slowed down and stopped. the early mixture of hydrogen and helium remained as the primary composition of matter throughout the cosmos. At this point, however, the universe was still far too hot for atoms to form. Electrons moved freely through space, constantly scattering off photons and atomic nuclei. Light could not travel very far without colliding with charged particles. The entire universe behaved like a glowing fog of plasma. This situation lasted for hundreds of thousands of years. During that time, the universe continued expanding and cooling gradually. Temperatures slowly dropped from billions of degrees to thousands of degrees. Although this was a dramatic change compared with the early moments, it still meant the cosmos remained hotter than most stellar surfaces. Eventually, the temperature fell to around 3,000 degrees Celsius. At this point, conditions allowed electrons to combine with atomic nuclei and form neutral atoms for the first time. Hydrogen atoms appeared throughout the universe, along with helium atoms created earlier during nuclear synthesis. Once electrons became bound within atoms, photons could travel freely without constantly scattering. Light that had been trapped inside the cosmic plasma suddenly began moving through space unobstructed. This event is known as recombination. The radiation released at that moment still exists today. As the universe continued expanding, the wavelength of that ancient light stretched and cooled. Today we observe it as the cosmic microwave background, a faint glow filling all of space. That radiation represents the oldest light we can currently detect. Measurements of the cosmic microwave background provide scientists with detailed information about the early universe. Tiny variations in temperature within this radiation reveal how matter was distributed shortly after recombination. Over billions of years, those small fluctuations grew under the influence of gravity. Regions containing slightly more matter pulled in surrounding gas, eventually forming the first stars and galaxies. Looking back at the earliest phases of the universe reveals something remarkable. The hottest place that has ever existed was not a star, a black hole, or a supernova. It was the universe itself during its earliest moments. Every region of space shared those extreme temperatures. Instead of isolated hotspots, the entire cosmos existed as a uniform ocean of energy and particles at unimaginable heat. As expansion continued, that energy spread outward, cooling the universe and allowing structure to form. Stars ignited, galaxies assembled, planets, and eventually life appeared within certain regions. Yet the extreme temperatures of the early universe did not disappear entirely from scientific study. Although we cannot travel back to those moments directly, physicists have found ways to recreate tiny pieces of that ancient environment here on Earth. It might seem surprising that some of the most extreme temperatures ever created did not occur in distant galaxies or violent stellar explosions, but inside enormous laboratories here on Earth. While the universe produced unimaginable heat during its earliest moments, scientists have found ways to briefly recreate similar conditions using machines designed to accelerate particles to extraordinary speeds. These machines are known as particle accelerators. Particle accelerators are among the largest scientific instruments ever built. Their purpose is to take tiny particles, often protons or atomic nuclei, and push them to incredibly high velocities. By accelerating these particles and then allowing them to collide, scientists can release tremendous amounts of energy in a very small space. When those collisions occur, the energy concentrated in the impact zone can momentarily create temperatures far beyond those found in stars or supernova remnants. The most famous of these machines is the Large Hadron Collider, often called the LHC. The LHC is located near Geneva, Switzerland, in a circular tunnel about 27 kilometers in circumference. This enormous ring sits deep underground and contains powerful magnets that guide and accelerate beams of particles moving close to the speed of light. Inside the collider, beams of protons or heavier atomic nuclei travel in opposite directions around the ring. When the beams reach the desired energy, they are directed to cross paths at specific points where detectors are positioned. At those crossing points, the particles collide. These collisions occur at velocities extremely close to the speed of light. When two particles meet with such energy, their kinetic energy transforms into a burst of new particles and radiation. According to Einstein's equation, energy can convert directly into mass. The collision zone briefly contains a dense cloud of newly created particles moving in every direction. During these tiny instants, temperatures can reach extraordinary levels. In certain experiments involving collisions between heavy ions, such as lead nuclei, scientists have produced temperatures exceeding several trillion degrees Celsius. That is far hotter than the interior of any star, and hotter even than many supernova explosions. These extreme conditions last for only a fraction of a second, but they allow physicists to study how matter behaves when energy density becomes incredibly high. The reason scientists aim for such extreme temperatures is to recreate a particular state of matter that existed in the early universe. Earlier we discussed the Quark-gluon plasma that filled the cosmos shortly after the Big Bang. Under ordinary conditions, quarks are confined within protons and neutrons. They cannot move freely because they are bound together by the strong nuclear force. But when temperatures rise above a certain threshold, that confinement breaks down. In the intense environment created by particle collisions, protons and neutrons can briefly melt into their fundamental components. Quarks and gluons move freely within a tiny region of space, forming a fluid-like state known as quark-gluon plasma. This state of matter behaves in fascinating ways. Rather than acting like a gas of independent particles, quark-gluon plasma flows more like a nearly perfect liquid. Experiments have shown that it has extremely low viscosity, meaning it moves with very little resistance. This discovery surprised many scientists because they initially expected the plasma to behave more like a thin gas. Studying quark-gluon plasma helps physicists understand how matter transitioned from its earliest form into the particles and atoms that make up the modern universe. In the first microseconds after the Big Bang, the entire universe was filled with this plasma. As the universe expanded and cooled, quarks combined into protons and neutrons, eventually leading to the formation of atomic nuclei. By recreating similar conditions in the laboratory, researchers can investigate how that transition occurred. The detectors surrounding particle collisions are among the most complex scientific instruments ever built. When particles collide inside an accelerator, they produce showers of new particles that spread outward in all directions. Detectors track the paths, energies, and identities of these particles. By analysing the resulting data, scientists reconstruct what happened during the collision. The amount of information collected in each experiment is enormous. Thousands of collisions may occur every second. Each collision generates large volumes of data describing the behaviour of dozens or even hundreds of particles. Powerful computers analyse these events, searching for patterns that reveal new insights about fundamental physics. The detectors themselves are built in layers, each designed to measure different aspects of the collision. Some layers track the paths of charged particles using sensitive electronic sensors. Others measure energy by absorbing particles and recording the resulting signals. Still others detect particles that rarely interact with matter, such as neutrinos. Together, these systems allow scientists to observe events occurring within regions smaller than an atomic nucleus. Despite the complexity of these machines, the basic idea remains straightforward. Concentrate energy into an extremely small space for an extremely short time. When that happens, temperatures rise dramatically. The temperature reached in heavy ion collisions at the LHC and similar accelerators has been estimated at around 5 trillion degrees Celsius. That number represents one of the highest temperatures ever measured in a controlled experiment. At such temperatures, ordinary matter cannot exist. Instead of atoms or even atomic nuclei, the collision region contains a dense mixture of quarks, gluons, and other fundamental particles moving with tremendous energy. Although these conditions exist for only a brief instant, they provide a valuable window into the physics of the early universe. Particle accelerators around the world contribute to this research. In addition to the LHC, Facilities such as the relativistic Heavy Ion Collider in the United States conduct experiments specifically designed to study quark-gluon plasma. Each experiment adds new data that helps scientists refine their understanding of high-energy matter. These experiments also reveal how energy transforms into new forms of matter. During collisions, particles not normally present in everyday environments can appear. Some exist only briefly before decaying into other particles. Observing these processes helps physicists test theoretical models describing the fundamental forces of nature. One of the most famous discoveries associated with particle accelerators occurred in 2012 when scientists confirmed the existence of the Higgs boson. The Higgs boson plays a crucial role in explaining why certain particles have mass. Its discovery provided strong support for the standard model of particle physics, the framework scientists use to describe the behavior of fundamental particles. Although the Higgs boson itself is not directly related to extreme temperatures, its discovery highlights how particle accelerators allow scientists to explore conditions and phenomena impossible to observe under ordinary circumstances. What makes these experiments especially interesting in the context of temperature is the scale difference involved. The region where a particle collision occurs is unimaginably small. It is far smaller than a grain of sand, smaller even than an atom. Yet within that tiny space, temperatures surpass those found in most cosmic environments. The reason this is possible lies in energy density. By concentrating large amounts of energy into a microscopic volume, scientists create conditions where particles move with incredible energy. Temperature, which measures the average kinetic energy of particles, rises accordingly. Even though the high temperature lasts only for a brief instant, it represents a genuine physical state that can be studied and measured. These laboratory experiments remind us that extreme heat is not limited to distant stars or galaxies. Under the right conditions, the fundamental laws of physics allow such temperatures to appear anywhere energy becomes sufficiently concentrated. Imagine matter heated so intensely that even the particles inside atomic nuclei begin to separate. Not atoms breaking apart, but the protons and neutrons themselves dissolving into their most fundamental ingredients. That is the state physicists call quark-gluon plasma, and it represents one of the hottest forms of matter ever produced. Under ordinary conditions, the structure of matter is surprisingly stable. Atoms consist of electrons orbiting a nucleus made of protons and neutrons. Those protons and neutrons are themselves built from smaller particles called quarks, which are held together by gluons. The strong nuclear force binds them so tightly that individual quarks are never observed on their own in everyday environments. Even inside stars, where temperatures reach millions of degrees, protons and neutrons remain intact. Their internal structure stays locked together by that powerful force. But temperature measures the energy of moving particles, and if the energy becomes high enough, even the strong force can be temporarily overcome. When temperatures climb into the trillions of degrees, the boundaries between protons and neutrons begin to dissolve. The quarks inside them are no longer confined to individual particles. Instead, they move freely within a dense, energetic mixture, along with the gluons that normally hold them together. That mixture is quark-gluon plasma. In this state, matter behaves very differently from anything familiar in daily life. Instead of solid objects, liquids, or gases made of atoms, the material becomes a kind of particle fluid composed of the building blocks of nuclear matter. Understanding this unusual state helps scientists study the earliest moments of the universe. Shortly after the Big Bang, the universe was far too hot for protons and neutrons to exist as stable particles. The entire cosmos was filled with quark-gluon plasma. As the universe expanded and cooled, quarks gradually combined into protons and neutrons, allowing atomic nuclei and eventually atoms to form. For a long time, that ancient phase existed only in theory. Physicists predicted that such a state should appear at extremely high temperatures, but recreating those conditions seemed impossible. The temperatures required are far beyond those found in everyday environments, and even the cores of stars are not hot enough. Eventually, particle accelerators provided a way to approach those conditions. When heavy atomic nuclei are accelerated to nearly the speed of light and smashed together, enormous amounts of energy are concentrated in a tiny region of space. For a brief instant, the energy density becomes high enough to melt protons and neutrons into quark-gluon plasma. These collisions occur in facilities such as the relativistic Heavy Ion Collider in the United States and the Large Hadron Collider in Europe. Inside these machines, beams of heavy ions, often lead or gold nuclei, race through circular tunnels guided by powerful magnets. When two beams collide, the impact creates a microscopic fireball where temperatures can exceed several trillion degrees Celsius. The fireball expands and cools almost immediately, but during that tiny fraction of a second, quark-gluon plasma exists. Because the state disappears so quickly, scientists cannot observe it directly in the way one might examine a solid object. Instead, they study the particles produced as the plasma cools and transitions back into ordinary matter. Detectors surrounding the collision point record the paths, energies, and identities of thousands of particles emerging from each event. By analysing patterns in these particles, researchers reconstruct how the plasma behaved before it cooled. One of the most surprising discoveries about quark-gluon plasma is that it behaves more like a liquid than a gas. At first, physicists expected the freed quarks and gluons to move independently, forming a chaotic cloud of particles. Instead, experiments showed that the plasma flows smoothly, almost like a perfect fluid. In fact, quark-gluon plasma appears to have one of the lowest viscosities ever measured. Viscosity describes how easily a fluid flows. Water flows easily compared with honey, which has higher viscosity. Quark-gluon plasma flows even more freely than water. The particles inside it move collectively, responding to pressure gradients and forming patterns similar to fluid currents. This behavior suggests that the strong force between quarks and gluons remains influential even in this high-energy state. Rather than moving entirely independently, the particles still interact strongly with one another, creating coordinated motion across the plasma. The discovery reshaped scientists' understanding of how fundamental particles behave under extreme conditions. Another fascinating aspect of quark-gluon plasma involves the enormous pressure within the collision zone. When two heavy nuclei collide at high energy, the resulting plasma expands rapidly outward. The pressure gradients created during the collision cause particles to move in characteristic patterns that detectors can measure. One such pattern is known as elliptic flow. Because the overlapping region between the colliding nuclei has an elongated shape, the plasma expands more easily in certain directions than others. This directional expansion leaves measurable signatures in the particles that emerge. Studying these patterns helps researchers determine properties such as the viscosity and temperature of the plasma. Although the plasma exists for only a tiny fraction of a second, its properties reveal important details about the physics of the early universe. The temperatures reached in these experiments are astonishing. The quark-gluon plasma created in heavy ion collisions can reach temperatures around 5 trillion degrees Celsius. To put that into perspective, the core of the Sun reaches about 15 million degrees. Even supernova explosions typically reach temperatures in the billions of degrees. The plasma produced in particle accelerators is hundreds of thousands of times hotter than the center of our star. Despite these incredible temperatures, the region where the plasma forms is incredibly small. The fireball created in a heavy ion collision measures only a few femtometers across. A femtometer is 1 quadrillionth of a meter, roughly the size of an atomic nucleus. Within that tiny space, however, energy becomes so concentrated that matter enters one of the hottest states ever observed. Because the plasma cools almost instantly, it transitions back into ordinary particles such as protons, neutrons, and mesons. These particles fly outward from the collision point and are captured by detectors. By analysing their trajectories and energies, scientists reconstruct the evolution of the plasma during its brief existence. Each collision provides a tiny snapshot of high-energy physics. Researchers repeat the experiments millions of times, gathering enough data to reveal consistent patterns. Over years of study, these experiments have confirmed that quark-gluon plasma behaves as predicted in many theoretical models. The work continues as physicists refine their understanding of this remarkable state of matter. Exploring quark-gluon plasma not only teaches us about the early universe, but also helps improve theories describing the strong nuclear force. This force governs how quarks interact with each other and plays a central role in the structure of matter. Understanding it more fully could lead to deeper insights into the behavior of fundamental particles. Although quark-gluon plasma represents one of the hottest forms of matter ever produced, it does not occur naturally in most places today. The universe cooled rapidly after the Big Bang, allowing protons and neutrons to form and remain stable. Only in rare environments, such as the cores of neutron star collisions or the tiny fireballs created in particle accelerators, do conditions briefly return to this primordial state. Still, the fact that humans can recreate such extreme temperatures in laboratory experiments reveals something remarkable about the power of modern science. With carefully designed machines and detectors, scientists can study matter under conditions similar to those that existed when the universe was less than a microsecond old. Sometimes the hottest conditions in the universe are not found in a place you can point to, like the surface of a star or the swirling gas around a black hole. Instead, they exist inside individual particles racing through space with extraordinary energy. These particles are known as cosmic rays. Despite the name, cosmic rays are not rays in the usual sense. Most of them are individual atomic nuclei, often just single protons, that travel across the universe at speeds extremely close to the speed of light. They originate from some of the most energetic events known in astrophysics, and carry enormous amounts of energy packed into a single particle. Cosmic rays are constantly arriving at Earth. Every second, particles from deep space strike our atmosphere. Most pass unnoticed, colliding with atoms high above the surface and producing cascades of secondary particles. These particle showers spread through the atmosphere before disappearing long before they reach the ground. The majority of cosmic rays have relatively modest energies compared with the most extreme examples. Many are produced by ordinary astrophysical processes such as supernova explosions or strong magnetic activity around stars. But a small fraction of cosmic rays possess energies so enormous that they challenge our understanding of how the universe accelerates particles. These are known as ultra-high energy cosmic rays. Some of these particles carry as much kinetic energy as a well-thrown baseball, yet all of that energy is concentrated within a single atomic nucleus. The comparison may sound unusual, but it illustrates just how energetic these particles can be. Imagine shrinking the energy of a thrown ball down to something far smaller than an atom. That is roughly the scale involved. To reach such energies, cosmic rays must be accelerated by some of the most powerful environments in the universe. One likely source involves supernova remnants. When a massive star explodes, the expanding shock wave moves outward through surrounding gas at tremendous speed. Charged particles caught in these shock waves can bounce back and forth across the shock front, gaining energy with each pass. Over time, this process can accelerate particles to very high speeds. Another possible source involves the powerful magnetic fields near neutron stars or black holes. In those regions, intense gravitational and magnetic forces can fling charged particles outward with enormous energy. Active galaxies containing quasars may also accelerate particles to extreme speeds through interactions with their enormous jets of plasma. Once accelerated, cosmic rays begin long journeys through interstellar and intergalactic space. Unlike photons, which travel in straight lines, charged particles are affected by magnetic fields. The universe is threaded with weak magnetic fields associated with stars, galaxies, and clusters of galaxies. As cosmic rays travel, these magnetic fields deflect their paths. The result is that by the time a cosmic ray reaches Earth, it may have taken a complex and winding route through space. This makes it difficult to determine exactly where a particular particle originated. Still, by studying large numbers of cosmic rays and analysing their energies, scientists can learn about the environments that produced them. When cosmic rays reach Earth, they encounter the atmosphere. A high-energy cosmic ray colliding with an atmospheric atom produces a chain reaction. The collision generates secondary particles such as pions, muons, and electrons. These particles in turn collide with other atoms, creating a shower that spreads outward as it travels downward. Large detectors on the ground can observe these showers. Some observatories cover vast areas in order to capture the rarest and most energetic events. One of the largest is the Pierre Auger Observatory in Argentina, which spreads across thousands of square kilometers of open land. The observatory uses hundreds of detectors placed across the landscape to measure the arrival of particle showers. When a cosmic ray strikes the atmosphere and creates a cascade of particles, the detectors record the signals produced as those particles pass through. By analysing the pattern of signals across many detectors, scientists can reconstruct the direction and energy of the original cosmic ray. These measurements have revealed that some cosmic rays possess energies far greater than those produced in human-made particle accelerators. The most energetic cosmic ray ever recorded carried an energy of about 300 billion electron volts. That value is so large that scientists gave the event a memorable nickname, the "Oh my God" particle. The name reflects the reaction researchers reportedly had when they first calculated its energy. Although cosmic rays themselves are individual particles, the energy they carry can be interpreted as a kind of temperature. In physics, temperature relates to the average kinetic energy of particles in a system. A single cosmic ray particle with enormous kinetic energy can be compared to particles in an extremely hot gas. If many particles had similar energies, the resulting system would correspond to temperatures far beyond those found in most astrophysical environments. In that sense, cosmic rays represent particles carrying fragments of the universe's most extreme energies across vast distances. Their journeys can last millions or even billions of years. Some cosmic rays may originate from distant galaxies, travelling through intergalactic space before eventually encountering Earth. During their travels, they interact occasionally with radiation fields and magnetic fields, gradually losing energy. Despite these losses, many still arrive with enormous energies intact. Studying cosmic rays helps scientists explore how the universe accelerates particles and distributes energy across space. Their interactions with Earth's atmosphere also provide a natural laboratory for particle physics. When cosmic rays strike atmospheric atoms, the resulting particle showers resemble miniature versions of the collisions studied in particle accelerators. Before large accelerators were built, many discoveries in particle physics came from studying cosmic rays. In fact, several fundamental particles, including the positron and the muon, were first detected through cosmic ray experiments. Even today, cosmic rays continue to provide valuable information about high-energy processes occurring far beyond our solar system. Although cosmic rays carry enormous energy, they do not represent a permanent hot environment like a star or accretion disk. Instead, they are moving packets of energy travelling through space. Their significance lies in the insight they provide into the universe's most energetic accelerators. Some of those accelerators involve collapsing stars, powerful magnetic fields, or the enormous gravitational engines at the centres of galaxies. After exploring the heat of stars, exploding supernovae, neutron stars, black hole accretion disks, and even the tiny fireballs created in particle accelerators, a natural question begins to appear. Can temperature keep increasing forever? Or is there some ultimate limit, a point beyond which heat cannot rise any further? It might feel intuitive to assume there is no limit. If temperature simply measures the energy of moving particles, then perhaps adding more and more energy should always raise the temperature. After all, a pot of water can be heated higher and higher if you continue adding heat. But when physicists began examining extreme conditions more carefully, they realise that the situation becomes more complicated at very high energies. At ordinary temperatures, increasing heat simply means particles move faster. Molecules vibrate more vigorously, atoms collide more energetically. If enough energy is added, solids melt into liquids and liquids boil into gases. Continue heating even further, and atoms themselves lose their electrons, forming plasma. So far, each step simply involves giving particles more energy. But eventually the energy becomes so large that the structure of matter begins to change in deeper ways. At temperatures of trillions of degrees, protons and neutrons themselves break apart into quarks and gluons, forming the quark-gluon plasma discussed earlier. Matter no longer resembles atoms or nuclei. Instead, it becomes a dense fluid of fundamental particles. Even then, the question remains, could temperatures continue climbing indefinitely if enough energy were added? To answer this, physicists look at how energy behaves when it becomes extremely concentrated. Temperature corresponds to the average kinetic energy of particles. But as energy increases, something interesting begins to happen. New particles can appear. According to Einstein's famous relationship between mass and energy can transform into matter. When enough energy exists in a small region, it can produce pairs of particles and antiparticles. In extremely energetic environments, energy no longer goes entirely into making particles move faster. Instead, part of that energy begins creating additional particles. The system becomes crowded with more and more matter. This process acts as a kind of pressure valve for extreme energy densities. Rather than allowing particle speeds to increase without bound, the energy spreads out by producing additional particles. As temperatures rise further, particle interactions become increasingly complex. New particle types appear, collide, and decay into other particles. The number of possible interactions grows rapidly. The system becomes a dense and chaotic environment, where energy constantly shifts between motion and particle creation. Physicists studying high-energy environments realize that there might be a theoretical limit beyond which temperature cannot be meaningfully defined, using the ordinary concepts of particle motion. The idea of a maximum temperature arises when gravity enters the picture. Under normal conditions, gravity is extremely weak compared with other forces acting on particles, but when energy densities become enormous, gravity begins to play a much larger role. Energy itself contributes to gravity. If enough energy is packed into a sufficiently small space, the gravitational effects become significant. In fact, if energy concentration becomes high enough, it could theoretically create a tiny black hole. This leads physicists to consider the scale where quantum mechanics, gravity, and particle physics all become equally important. That scale is defined by a set of natural units known as the Planck units, named after the physicist Max Planck. Planck units arise from combinations of fundamental constants: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. These constants describe the basic behavior of the universe. From them, physicists derive quantities such as the Planck length, Planck time, and Planck temperature. The Planck temperature represents an estimated upper limit to temperature. Its value is roughly 1.4 times 10 to the power of 32 Kelvin. That number is so large that it is difficult to comprehend. It is far hotter than the temperatures produced in particle accelerators, hotter than any supernova, and hotter even than the conditions believed to exist shortly after the Big Bang. At temperatures approaching this level, the known laws of physics begin to break down. Gravity becomes as strong as the other fundamental forces. Quantum fluctuations of space-time itself become significant. The smooth geometry of space and time described by general relativity may no longer apply. Instead, space-time may behave more like a fluctuating quantum structure. Physicists do not yet have a complete theory that describes this regime. General relativity describes gravity very well on large scales, such as stars and galaxies. Quantum mechanics describes particles and forces on very small scales. But combining these two frameworks into a single theory of quantum gravity remains one of the major challenges in modern physics. At temperatures near the Planck temperature, both effects become equally important. Without a complete theory of quantum gravity, scientists cannot fully describe what matter or energy would do under those conditions. One possibility is that our current concept of temperature would cease to be meaningful. Temperature relies on the idea of particles moving within space-time. But if space-time itself becomes unstable or fluctuates at the quantum level, the entire framework used to define temperature may no longer apply. In other words, beyond this point, asking about temperature may not make sense in the usual way. The Planck temperature therefore represents not just a physical limit, but also a boundary in our understanding. It marks the point where current theories stop providing reliable predictions. Interestingly, the early universe may have briefly reached temperatures near this limit. Immediately after the Big Bang, when the universe was extremely dense and small, temperatures could have approached the Planck scale. As the universe expanded, it cooled rapidly, moving away from that extreme regime into the more familiar physics we observe today. Because the universe cooled so quickly, those earliest conditions lasted only a tiny fraction of a second. Today, no known natural process produces temperatures anywhere near the Planck temperature. Even the most energetic cosmic events fall far short of this theoretical boundary. Yet the concept of a maximum temperature still provides insight into the nature of the universe. It reminds us that the laws of physics may have deeper layers that remain hidden under normal conditions. Only in the most extreme environments do those deeper principles begin to reveal themselves. Physicists continue searching for clues about how the universe behaves at these extremes. Experiments with particle accelerators, observations of black holes, and studies of the cosmic microwave background all contribute pieces of the puzzle. Each discovery helps refine our understanding of energy, matter, and the fundamental forces governing the cosmos. For now, the Planck temperature remains a theoretical frontier rather than an observed reality. But thinking about such extremes provides a useful perspective. The heat of stars, supernovae, and even quark-gluon plasma might seem unimaginably intense. Yet compared with the Planck scale, those temperatures occupy only a small portion of the possible range allowed by physics. The universe began in a state far hotter than anything we observe today. There comes a point when exploring the extremes of heat where familiar comparisons stop being useful. Earlier we talked about temperatures in stars, then in supernova explosions, and then the trillions of degrees produced in particle accelerators. Each step seemed impossibly hotter than the one before it. Yet even those astonishing temperatures are still far below what physics suggests might be the ultimate limit. That theoretical boundary is the Planck temperature. The Planck temperature represents the point where our current understanding of physics begins to break down. It is not simply another very large number on the temperature scale. Instead, it marks the region where the fundamental rules describing matter, energy, gravity, and space itself can no longer be treated separately. To understand why this temperature matters, it helps to look at how physicists think about the basic structure of the universe. Modern physics relies on two enormously successful frameworks. One of them is quantum mechanics, which describes how particles behave on extremely small scales. The other is general relativity, Einstein's theory explaining how gravity shapes space and time on large scales. Both theories have been tested repeatedly and have proven incredibly accurate within their respective domains. Quantum mechanics explains the behavior of atoms, electrons, and subatomic particles. It predicts how particles interact through forces such as electromagnetism and the strong nuclear force. General relativity explains how massive objects warp space-time and create gravity. It accurately describes the motion of planets, the bending of light near massive bodies, and the structure of black holes. But there is a problem. The two theories are not easily combined. In everyday conditions, this conflict does not cause trouble. Most physical situations involve either very small particles where gravity is negligible, or very large objects where quantum effects are insignificant. However, when energy densities become extremely high, both theories must operate at the same time. That happens at the Planck scale. The Planck scale is defined using three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When these constants are combined mathematically, they produce a set of natural units that describe the smallest meaningful scales of space, time, and energy. Among these values are the Planck length, the Planck time, and the Planck temperature. The Planck temperature is roughly 1.4 times 10 to the power of 32 Kelvin. Writing it out reveals just how enormous that number is: 100 quintillion degrees. At temperatures approaching this level, the energy contained in individual particles becomes so large that gravity begins influencing particle interactions in a way that ordinary physics cannot describe. In simpler terms, particles become energetic enough that their gravitational effects are no longer negligible. At that point, space-time itself may begin to fluctuate. Normally we imagine space as a smooth stage where physical events take place, but quantum theory suggests that at extremely small scales, even empty space is not truly empty. Instead, it contains tiny fluctuations of energy that appear and disappear constantly. At Planck scale energies, these fluctuations could become so intense that space-time behaves more like a frothy, constantly shifting structure rather than a smooth background. Physicists sometimes describe this idea as quantum foam. In such conditions, the ordinary concepts used to measure distance and time might lose their meaning. The geometry of space-time could fluctuate so rapidly that it becomes impossible to define stable coordinates. And if space-time itself becomes unstable, then our usual definitions of motion and energy, both essential for defining temperature, may no longer apply. This is why the Planck temperature is often described as the ultimate edge of physics. Beyond this point, the equations used in modern science cannot reliably predict what happens. Some researchers believe that reaching this temperature would require concentrating enormous amounts of energy into an extremely small region. If enough energy were packed together, gravity might form microscopic black holes. These tiny black holes would appear and disappear extremely quickly, constantly forming and evaporating through quantum processes. Others suggest that at such extreme energies, the fundamental forces of nature may merge into a single unified interaction. Today, we recognize four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But theoretical models suggest that at very high energies, these forces may have once been unified. In the earliest moments after the Big Bang, the universe may have existed in such a unified state. As it expanded and cooled, the forces gradually separated into the distinct interactions we observe today. The Planck temperature may correspond to the energy scale where this unification originally occurred. Understanding that regime could reveal deeper principles governing the universe. Unfortunately, testing these ideas directly remains far beyond current technological capabilities. Even the most powerful particle accelerators ever built produce energies trillions of times lower than those associated with the Planck scale. Creating Planck temperature conditions in a laboratory would require machines vastly more powerful than anything humans have constructed. For now, scientists study this frontier through theoretical physics. Researchers develop mathematical models attempting to unify gravity with quantum mechanics. Several candidate theories exist, including string theory and loop quantum gravity. Each proposes different ways that space-time and particles might behave at Planck scale energies. Although these theories remain incomplete, they provide hints about how the universe may operate at its most extreme limits. One intriguing possibility is that the Planck temperature was reached only once in the history of the universe. During the earliest fraction of a second after the Big Bang, the universe was compressed into a tiny volume with enormous energy density. At that time, temperatures may have approached the Planck scale. If that is correct, then the laws of physics we observe today emerged as the universe cooled and expanded away from that extreme state. This idea suggests that the familiar structure of particles, forces, and space-time evolved from conditions that were once far more chaotic and energetic. The early universe might have passed through a series of transitions as it cooled. At first, the fundamental forces separated. Then quarks combined into protons and neutrons. Later, nuclei formed, followed eventually by atoms. Over billions of years, gravity gathered matter into stars and galaxies. All of that structure grew out of the cooling of a universe that began in a state of extraordinary heat. Thinking about the Planck temperature therefore connects two ideas. On one hand, it represents a theoretical upper limit of temperature. On the other hand, it marks the beginning of the thermal history of the cosmos. Everything we observe today exists because the universe cooled from that extreme starting point. At the beginning of the universe, heat was everywhere. Not just in one place, not concentrated inside a star or a galaxy, but spread through all of space. Every region of the cosmos existed in a state of intense energy. Particles collided constantly, radiation filled every direction, and the temperature was so high that the familiar structure of matter could not exist yet. Over time, however, something remarkable began to happen. The universe started to cool. This cooling did not occur because heat escaped into some external space. Instead, it happened because space itself was expanding. As the universe grew larger, the energy contained within it spread across a greater volume. When energy becomes more spread out, the average energy of particles decreases and temperature falls. In other words, the universe cooled because it grew. During the earliest moments after the Big Bang, temperatures were unimaginably high. Earlier we explored the idea that the universe may have reached temperatures close to the Planck scale, the theoretical limit where our current understanding of physics begins to break down. Those extreme conditions did not last long. The universe expanded extremely rapidly during its first moments. As expansion continued, temperatures dropped quickly, allowing new structures to form. Within the first tiny fraction of a second, the universe was filled with quarks, gluons, electrons, photons, and other fundamental particles. These particles moved through a dense plasma where collisions occurred constantly. As the universe cooled slightly, quarks began combining into protons and neutrons. That step represented a major change in the structure of matter. Instead of a fluid of free quarks, the universe now contained stable building blocks that could later form atomic nuclei. But the cooling process continued. During the first few minutes after the beginning, temperatures remained extremely high, billions of degrees. In that environment, protons and neutrons collided frequently enough to form the nuclei of light elements. This period is known as Big Bang nucleosynthesis. Hydrogen nuclei, consisting of single protons, formed in enormous quantities. Some protons and neutrons combined to form helium nuclei, containing 2 protons and 2 neutrons. Small traces of lithium and other light elements also appeared. These nuclei would later become the raw material for stars and galaxies. Even after this stage, the universe remained a hot plasma. Electrons were still moving freely, unable to remain bound to atomic nuclei because the surrounding radiation was too energetic. Photons scattered constantly from charged particles, filling space with an opaque glow. Light could not travel far without colliding with something. The universe during this period would have appeared like a bright fog. This phase lasted for hundreds of thousands of years. During that time, expansion gradually reduced the temperature further. Eventually, the temperature fell to around 3,000 degrees Celsius. At that point, electrons could finally combine with nuclei to form stable atoms. Hydrogen atoms formed throughout the universe, along with helium atoms created earlier during nucleosynthesis. This transition changed the universe dramatically. With electrons now bound inside atoms, photons could travel freely through space without constant scattering. The bright fog cleared, and light began moving across the cosmos uninterrupted. The radiation released at that moment still fills the universe today. As the universe continued expanding, the wavelengths of that radiation stretched and cooled. What once glowed with visible light now appears as faint microwave radiation, known as the cosmic microwave background. This radiation represents the oldest light we can observe. Measurements of the cosmic microwave background provide scientists with a snapshot of the universe when it was only about 380,000 years old. Although the universe had cooled dramatically compared with its earliest moments, it was still hotter than most environments we encounter today. Yet cooling continued steadily. Over millions of years, the temperature of the universe dropped further as expansion carried galaxies farther apart. Meanwhile, gravity began shaping the distribution of matter. Small variations in density that existed in the early universe gradually grew larger. Regions containing slightly more matter attracted additional gas and dust through gravitational pull. These growing clouds eventually collapsed under their own gravity. Inside those collapsing clouds, temperatures began rising again locally. Although the overall universe was cooling, gravity could concentrate matter in specific regions. As gas clouds contracted, the pressure and temperature in their centers increased. This process eventually ignited the first stars. These early stars formed hundreds of millions of years after the Big Bang. They were likely very massive and extremely hot compared with many stars seen today. Their formation marked the end of the universe's earliest dark ages. Once the first stars ignited, they began producing light and heat through nuclear fusion. Their radiation illuminated surrounding gas and influenced the formation of future generations of stars. Despite the birth of these hot stellar furnaces, the overall universe continued cooling. The expansion of space remained the dominant trend shaping cosmic temperature. Galaxies formed and evolved, stars ignited and died, and new elements were created through stellar fusion and supernova explosions. Yet throughout all these processes, the background temperature of the universe steadily declined. Today, the cosmic microwave background has cooled to about 2.7 Kelvin above absolute zero. That means the average temperature of empty space is just a few degrees above the coldest temperature physically possible. Compared with the fiery beginning of the universe, the modern cosmos is remarkably cool. Stars, planets, and other structures exist as isolated pockets of warmth, surrounded by vast regions of cold space. The sun, for example, shines with surface temperatures of thousands of degrees, yet the space between planets remains extremely cold. If sunlight didn't warm Earth's surface, our planet would quickly freeze in the darkness of space. This contrast highlights an important feature of the universe. Heat tends to spread out over time. Regions of high temperature gradually release energy into their surroundings. As energy spreads more evenly, temperature differences decrease. This process is related to the concept of entropy. Entropy measures the degree of disorder or randomness in a system. In many physical processes, entropy tends to increase over time. Energy spreads out and systems move toward more uniform states. The cooling of the universe reflects this principle on the largest possible scale. In the beginning, energy was concentrated in an extremely dense and hot state. As the universe expanded, that energy dispersed across an ever-growing volume. The result has been a gradual decline in the average temperature of the cosmos. Yet the story is not simply one of constant cooling. Within galaxies, gravity continues gathering matter into stars and other structures. These regions create localized pockets of intense heat. Stars burn for millions or billions of years before exhausting their fuel. Some end their lives quietly, while others explode as supernovae, briefly creating temperatures far hotter than their stellar cores. These processes recycle matter and energy through galaxies. The heat produced by stars powers many of the phenomena we observe in the universe today. It drives stellar winds, lights up nebulae, and shapes the environments where planets can form. Without the heat of stars, the universe would be a far darker and colder place. Still, even these sources of heat represent temporary phases. Stars eventually run out of fuel. When they do, they fade into compact remnants such as white dwarfs, neutron stars, or black holes. Over extremely long timescales, the number of active stars in the universe may gradually decline. As that happens, the cosmos could become even colder. Astronomers sometimes refer to the distant future of the universe as a period of gradual thermal decline. If star formation slows and eventually stops, the universe may enter an era dominated by faint stellar remnants and dark, cold space. But that future lies trillions of years ahead. For now, the universe still contains countless stars shining across billions of galaxies. Each of those stars contributes warmth and light to its surroundings, even as the background temperature of the cosmos continues its slow descent. Looking across the vast span of cosmic history reveals an extraordinary transformation. The universe began as a state of unimaginable heat, where particles collided in a dense ocean of energy. Over billions of years, expansion cooled that fiery beginning into the calmer cosmos we see today. And within that cooler universe, pockets of heat continue to appear wherever gravity gathers matter and ignites new stars. Heat might seem like a simple idea at first. Most people experience it in very ordinary ways: a warm cup of tea in the morning, sunlight heating the surface of the ground, the feeling of stepping outside on a hot summer afternoon. Yet temperature is not just a small detail of daily life. It is one of the most important factors shaping the entire universe. From the birth of stars to the formation of planets, from the chemistry of life to the evolution of galaxies, temperature quietly governs what can exist and what cannot. Understanding heat is therefore not only about discovering the hottest place in the universe, it is also about understanding why the universe looks the way it does, and why certain regions become capable of supporting complex structures like planets and living organisms. At the most basic level, temperature describes the motion of particles. Atoms and molecules are never truly still. Even in solid materials, particles vibrate constantly around their positions. As temperature increases, these vibrations grow stronger. In liquids and gases, particles move more freely, colliding and bouncing past one another. When temperatures become extremely high, atoms lose electrons and become plasma. And at even higher energies, atomic nuclei themselves can break apart into their fundamental components. Because temperature controls particle motion, it also determines which forms of matter can exist. Take water as a familiar example. At low temperatures, water becomes ice, where molecules lock into a rigid structure. As temperature rises, the molecules gain enough energy to break free from that structure, forming liquid water. Increase the temperature further, and the molecules escape into the air as water vapor. These transitions between solid, liquid, and gas are controlled entirely by temperature and energy. In the universe, similar principles apply to much larger systems. Clouds of gas drifting through galaxies behave differently depending on their temperature. Cold gas clouds can collapse under gravity to form stars. Hot gas, on the other hand, tends to expand outward rather than collapsing. Temperature therefore plays a direct role in determining where stars can form. In regions where gas remains cool and dense, gravity slowly gathers material together. Over time, these clouds contract, and the central temperature begins to rise. If enough mass accumulates, the temperature in the core becomes high enough for nuclear fusion to ignite. A star is born. Once fusion begins, the star generates enormous amounts of heat and radiation. This energy pushes outward, balancing the inward pull of gravity and stabilizing the star for millions or billions of years. Without reaching the necessary temperatures, fusion could never begin. This means temperature determines whether a cloud of gas remains a cold nebula or transforms into a glowing star. Temperature also influences the types of stars that form. Massive stars compress their cores more strongly, reaching higher temperatures that allow faster nuclear reactions. These stars burn brightly and live relatively short lives. Smaller stars reach lower core temperatures and burn fuel more slowly, allowing them to shine steadily for billions or even trillions of years. The balance between gravity and heat defines the life cycle of stars. Temperature continues to shape events even after stars die. When massive stars collapse and explode as supernovae, The extreme heat created during the explosion allows new elements to form. Atoms heavier than iron are forged in these fiery events and then scattered across space. These elements later become part of future stars, planets, and eventually living organisms. In this way, temperature influences the chemical richness of the universe. Without those intense bursts of heat during supernova explosions, many of the elements essential for life would never exist. Carbon, oxygen, calcium and iron all owe their presence to the nuclear reactions occurring inside stars and the explosive environments where those stars end their lives. Temperature also determines whether planets can form and remain stable. Planets begin as small grains of dust within rotating disks of gas surrounding young stars. These particles collide and stick together, gradually forming larger bodies. But if temperatures are too high near the star, volatile materials evaporate and cannot condense into solid particles. This is why rocky planets like Earth tend to form closer to stars, while gas giants often form farther away where temperatures are lower. The distribution of temperature within a planetary system shapes the types of worlds that appear. Once planets form, temperature continues playing a crucial role in determining their environments. Earth exists within a region around the Sun often called the habitable zone. In this region, temperatures allow liquid water to exist on the surface. Liquid water is essential for the chemistry of life as we know it. If Earth were significantly closer to the Sun, temperatures would rise high enough to evaporate oceans and create a runaway greenhouse effect similar to what happened on Venus. If Earth were much farther away, the planet might resemble Mars, where colder temperatures allow water to freeze or escape into space. This narrow range of temperatures highlights how sensitive planetary environments can be. Life depends not only on the presence of certain elements, but also on temperature conditions that allow complex chemistry to occur. Biological processes rely on molecules interacting with one another in precise ways. Proteins fold into specific shapes, chemical reactions occur at controlled speeds, and cellular structures remain stable only within certain temperature ranges. Too much heat disrupts these structures. Too little heat slows chemical reactions so much that biological processes cannot function effectively. This delicate balance explains why life on Earth thrives within a relatively narrow temperature range, compared with the extreme environments found elsewhere in the universe. Even so, life has proven remarkably adaptable. Some microorganisms survive in hot springs where temperatures exceed 90 degrees Celsius. Others inhabit deep ocean vents where superheated water emerges from beneath the sea floor. In colder environments, certain organisms can survive in frozen conditions where temperatures drop far below the freezing point of water. These examples demonstrate that life can tolerate a wider range of temperatures than once believed. Still, there are limits. Beyond certain extremes, the molecular machinery of life breaks down. Temperature also shapes planetary atmospheres. Warm temperatures allow gases to remain active and circulate through atmospheric systems. Heat drives winds, storms, and ocean currents, distributing energy across a planet's surface. On Earth, sunlight heating the equator creates temperature differences that drive atmospheric circulation. These circulation patterns influence climate, weather systems, and ocean currents. Without temperature differences, these dynamic systems would not exist. The importance of heat extends even beyond planets and stars. Galaxies themselves contain regions of hot gas that fill the space between stars. In clusters of galaxies, enormous clouds of plasma reach temperatures of tens of millions of degrees. These hot gases emit X-rays that astronomers use to map the distribution of matter within galaxy clusters. The temperature of this gas reveals how galaxies interact and evolve within their cosmic environments. Heat therefore acts as a tracer of energy across the universe. Wherever energy concentrates, temperature rises. Observing temperature differences allows scientists to identify the physical processes shaping stars, galaxies, and cosmic structures. Even the faint glow of the cosmic microwave background carries information about the early temperature of the universe. Tiny variations in that radiation reveal the initial conditions from which galaxies eventually formed. Temperature, in other words, leaves fingerprints throughout cosmic history. By measuring those thermal fingerprints, astronomers can reconstruct events that occurred billions of years ago. From the fiery birth of the universe to the gentle warmth of sunlight reaching Earth today, temperature has guided the evolution of the cosmos. Heat drives nuclear fusion in stars, powers atmospheric circulation on planets, and shapes the chemical reactions that allow life to exist. Without the right temperatures at the right times, the universe would look very different. Stars might never ignite, planets might never form, complex chemistry might never develop, and life, as far as we understand it, would never appear. So when we ask about the hottest places in the universe, we are really asking something deeper. We're exploring how temperature influences the structure and history of everything around us. From the blazing interiors of stars to the delicate warmth that allows life to flourish on a small blue planet, heat connects every scale of the cosmos. Somewhere out in the universe, at this very moment, a star is exploding. In another distant galaxy, gas is spiraling into a black hole, heating until it shines with intense X-rays. Far away from both of those places, a particle accelerated by an ancient supernova is racing through space at nearly the speed of a light, carrying enormous energy across millions of light years. The universe is filled with extraordinary heat. Throughout this journey, we have explored many of the places where temperature reaches astonishing levels. We looked at the warmth we experience on Earth and then moved outward to the Sun, our nearby stellar furnace. From there, the scale expanded to include hotter stars, violent supernova explosions, neutron stars compressed into city-sized spheres, and the brilliant disks of gas swirling around black holes. Each step revealed environments where particles move faster, collisions become more energetic, and matter enters increasingly extreme states. Then the story stretched even further. We explored quasars capable of shining brighter than entire galaxies. We examined the first moments after the universe began expanding, when everything existed in a state of intense heat. We saw how scientists recreate tiny fragments of those early conditions inside particle accelerators, producing temperatures of trillions of degrees for brief instants. And beyond even those extremes, physics suggests theoretical limits like the Planck temperature, where the very structure of space-time may begin to fluctuate and our current theories lose their certainty. All of these environments reveal something important. Heat is not just a property of a place, it is a measure of energy in motion. Wherever energy becomes concentrated, temperature rises. Wherever energy spreads out, temperature falls. The entire history of the universe can be understood through that simple idea. In the beginning, energy was compressed into a dense and incredibly hot state. As space expanded, that energy spread outward, cooling the cosmos over billions of years. Stars formed from collapsing clouds of gas, igniting new pockets of intense heat. Galaxies assembled, planets appeared, and eventually life emerged on at least one small world. Yet through all of these events, the overall trend has remained the same. The universe is cooling, not quickly on human timescales, but steadily across cosmic history. The fiery beginning has gradually given way to a calmer and colder cosmos. The background temperature of space today is only about 2.7 degrees above absolute zero. Most of the universe is filled with darkness and cold, interrupted here and there by the glowing warmth of stars. Those stars will not shine forever. Over extremely long periods of time, even the most massive stars exhaust their nuclear fuel. When they do, they collapse into remnants like white dwarfs, neutron stars, or black holes. Eventually, star formation itself may slow as galaxies use up the gas needed to create new stars. If the universe continues expanding for trillions of years, it may become a place where bright stellar fires grow rarer. The distant future could be dominated by faint stellar remnants and vast stretches of cold, dark space. But that future lies unimaginably far ahead. Right now, the universe still contains enormous energy. Billions of galaxies shine with countless stars. New stars continue forming inside glowing nebulae. Supernova explosions scatter heavy elements across space, creating the raw material for future planets. The cosmos remains an active and evolving place, and on a small planet orbiting an ordinary star, life has developed the ability to observe and understand that universe. From our vantage point on Earth, we can measure the temperatures of distant stars, detect X-rays from black holes, and recreate fragments of the early universe in underground laboratories. Using telescopes and detectors, we read the faint thermal signals left behind by cosmic events billions of years ago. Through these observations, we slowly piece together the story of heat across the universe. It is a story that stretches from the unimaginable fire of the Big Bang to the gentle warmth of sunlight touching the surface of our world. In a way, every warm moment we experience on Earth connects us to that larger cosmic history. The warmth of sunlight reaching your skin began as nuclear reactions deep inside the sun's core. The elements in your body were forged in the intense heat of ancient stars that lived and died long before our solar system formed. Even the atoms around you carry traces of those fiery cosmic origins. And now, as you listen quietly and imagine the vast scale of the universe, the warmth around you feels a little different. Because somewhere out there, the hottest places in existence continue burning with incredible energy. Yet across the immense span of cosmic time, the universe itself is slowly drifting away from those ancient fires. And tonight, under the calm glow of distant starlight, the cosmos feels just a little cooler than it once was.